All right, we might start.
Okay.
So welcome everyone to the fifth and final day of PyHEP 2021. I might just remind everyone of the workshop photo, of the details of which were sent out in the Slack and in the email. We've got a very interesting session of talks ahead of us today, in particular the second half of the day dealing with Julia, which is slightly unexpected, but I and others I'm sure are quite interested to hear how Julia and HEP fit together. Starting off, we have got Helena talking on using Python for HEP outreach. You could.
Yes, hi, let me share my slides.
Yes, excellent.
Okay, can you see it?
Yes.
Okay, let me put it into that mode. All right, so get started. So first of all, thank you for the opportunity of showing this here. It's a little bit on the unusual side because I will talk about a different aspect of Python, which is the social side of it. So I hope you will enjoy it. Let's get started. So I will start the talk talking a little bit about the Rio de Janeiro city to set the ground on why we want to use Python as an outreach tool. Then how the COVID pandemic impacted Brazil, in particular Rio, with a focus on the schools and the high schools. And then I will show you a couple of projects that we have for undergraduates and school and high school students, and with the focus of having it on the social side, so as an opportunity for the underprivileged kids from school and high school. And then I will conclude. So first, let's start with the Rio de Janeiro city. So it's a huge city. It has in its core 6 million inhabitants. And if we consider the immediate outskirts, so the immediate suburbs of the city, we make it to the double, so around 12 million people. And if you look here on the top right at the population by age group, then we see highlighted the ages between school, high school, and university attendance. And we see that it's a significant portion of the population. So to attend those, we have as public schools, we have around 2,000 public schools, and I will emphasize on the public side soon, that attends around 700,000 kids. And when we move to high school, this number goes down by 1/3. So we have around 700 high schools to attend around 250,000 teenagers. So we can have an idea already from this transition from school to high school that there is some sort of evasion, and we can interpret this one of the aspects of this might be the lack of opportunities for these kids. So let's take a look then at something that happens in the city, that we have not only the public system of schools, but we have a large portion of private schools as well. So there is a whole thing going on the private system. Let me start describing in images the situation of the public schools. It's not all, but this is more frequent than we would like it to happen. So this is the rooftop of a public school in a community in Rio, Favela da Maré. And this sign is saying, "School, please don't shoot." And it happened in 2019, but it happens every now and then, unfortunately, when there are police operations in these communities, and the police arrive in helicopters shooting in the communities. And here is a classroom of a public school, not particularly this one, but just to have an idea of a classroom in the public system. And on the opposite side of this, we have the private schools that are quite different, as you can see. So here on the on the bottom right is a picture of a private school with a very well-equipped lab and classrooms. And if you look further into the pictures, you will see how it can create social and racial bias in the society and of Rio in general. So we can ask ourselves, how can we create then opportunities for those kids that come from some of those public schools and high schools? But then, and we started the project, but then came the pandemic and all around the world. And in Brazil, we were hit very hard, and we had a very bad management of this COVID pandemic, as I'm sure you all know. We reached around a peak of 100,000 new cases per day in Brazil. And in Rio, we had peaks of around 2,000 new cases per day. That's huge. And unfortunately, it was very badly managed. So because of this, especially in Rio, with the high number of cases, we had the public schools that were closed for 1 full year. The private schools opened much earlier because they had the structure to do so, but not the public schools. And this 1 year without classes mean for many children, not even online classes, means nothing, 1 year without school. But now the vaccination program in Rio has included the teachers in the priority group of vaccination. So in principle now, all the teachers from all schools and high schools are vaccinated, and the schools are again slowly reopening. So that gives us some sort of hope. We can try to continue with our project to teach Python in schools in Rio, in the public schools. And then I want to talk just a little bit, very fast, about the university, so the State University of Rio, because it gives us the environment to do this kind of project, because it has a history of social engaging. So the State University of Rio was the first university to have a woman as a university dean, and it was the first university in Brazil to implement affirmative action quotas for the minorities. So also because of that, the State University of Rio historically receives many students from public schools. So we started actually this project as a way of trying to help some of these students to improve their learning skills with Python. So to use Python as a tool for that. And then with some of the projects we developed with the students at the university, we thought we could bring it to the high schools and then teach Python at the high schools and bring some of the tools we developed at the university as an outreach tool for PyHEP. So then I will talk a little bit, I will show actually a few of those projects that we have with the undergrad students. So they learn about PyHEP with Python and build tools to be used in the high schools. And the schools and high schools, we teach block programming, we have to start like very at a very simple level because many of those students don't even have access to a computer. So then after we teach block programming, we go to Python learning, we do workshops, and some of them have scientific grants. I will talk about it in one slide at the end. So this is an example of a couple of projects that we have in the undergrad level. This is one of our students, Gabriel, that did it. He started with feet on the Z-Peak, on the Z to Mu Mu. This is a notebook that is available in the CMS Open Data, and then he modified it to use a different fitting package. And then for fitting the signal, we wanted a convolution of 2 PDFs, and he did it by hand. Now we could, of course, improve this by using, for example, the ZFit package, as it was shown here in the workshop. But Gabriel has now moved on to do his master's with us, and this was his bachelor thesis, where he used also a notebook from the CMS Open Data to classify events of Higgs to ZZ to 4 leptons using the extreme gradient boost package. And here you can see on the light blue dots are the Higgs signal as his classification model, and the black dots are the backgrounds. And then another project we have with also undergrad students, it's this GUI that fits peaks on the dimuon spectrum of CMS Open Data as well. So the GUI shows, here you can see all the peaks, and then you have the chance to choose which resonance you want to fit, and then let me see. You can click a button to do the fit and choose which PDF to use and which initial parameters you want to give for the fit. And here the final fit for the Z-Peak. So this GUI is still in Portuguese. It's work in progress, but we like it quite a lot because we can also then use it for high school students to learn a little bit about HEP. So before the pandemic, we had a boiled down version of this GUI running with Bokeh on a server. But with the pandemic, we had to shut it down, and now we are looking to continue. We have already on the pipeline other students to take this project over, and then we would like them to put it in a package, to translate the GUI to English, and then include some other functionalities so we can use it as outreach in high schools. So then here it's my last slide before the conclusion. It's what we do on high school. So we start very simple with block programming, so they learn the logics. Then we go to the classic turtle module so that they can draw images, and then with this they learn like simple things like functions and data structure of Python. And then they moved on. Those 2 students, they started with us, they were very young, and now they have moved on to work on some a little bit more complex, like Monte Carlo methods and image pattern recognition. They are already in high school now. And we also do workshops. So the last one we had 5 afternoons with the same program, like 2 or 3 hours per afternoon. And now with the schools and high schools coming back, we are going to do an online workshop. So that brings me to the conclusions. So Python is not only a powerful programming language, as you know, but it can also have a social aspect, and we are exploring this facet of Python. We are very happy because the project got some funding, and with this we will be able to purchase laptops or Raspberry Pis or whatever we find fit to bring Python to schools and high schools, because up to now we have the students coming to the university lab to do the workshops, but we think we can also reach out to them and go directly to the schools. And then I was also asked if there are ways that the PyHEP community could help with this project. So one thing I thought is that we really like this peak GUI, so it would be really nice to have it, once we have it packaged, to have it running in other servers on other universities. So if you're interested, please contact us at these emails here. So that's it. That's all for me. Thank you.
Thank you very much, Helena. Now, there's a few questions over on the Slido, if you'd like to bring up that window. So the link should be in the chat, the Zoom chat.
Okay, let me. The Slido, join discussion in Slack. No, Slido. Okay.
If you could screen share that so we can read the questions too, that would be great.
Sure. They're coming up here. I think it's this one. Did I get the right?
Yep, just click over to the Q&A on the top part of the screen. Yes, and maybe zoom in a little bit. Excellent, thank you.
I'd like to understand how PyHEP can engage better and more explicitly. Yes, so for example, when we have this Python GUI package, it would be nice to have it running on servers on other universities, if that's possible. I don't know, but I think we can also, I let my contacts there, we can also think of ways of collaborating on different topics and projects. So the undergrad students, I think most of them don't have language problems with English, so we could collaborate then. For the high school students, I think it's a little bit more difficult because of the language, but we can also do the intermediation. So the other question, have you looked at carpentries at all? No, actually not. Thank you very much. I'm gonna look into it. What is affirmative action? Accepting students some other way based on the financial situation of the family or something else? So the affirmative action that I mentioned from the state university is that they created quotas for both social economic quotas as racial quotas. So you can declare yourself as a Brazilian Indian, for example, and there is an amount of quota that is designed for you at the university. So it's both racial and financial. How could PyHEP community help you out with this project. Yes, so as I mentioned already, we can start collaborations, working on projects together. I've let the contacts of the project there, so please contact us. And I hope we will manage to have at least the GUI running soon. And if we can have it running other places, that would be great. I think
there was
I've answered.
one final question from Ben that was just added.
What is the rationale from your students when they start analyzing data and making plots? Oh, they are very enthusiastic. It's a very rewarding project because we all have a lot of fun. It's really nice. They're very enthusiastic and they produce really nice results.
All right. I think that is all of the. Oh, actually, one final. If you scroll down, oh, yeah, there we go.
No, we don't have. So, how many students go on to engage with science as a result of the classes? We are not very good yet on keeping track of the statistics, but we should. At the undergrad level, we had a few that actually continue on and go to do their masters or PhDs with us, but we should keep track, yes. Okay, so I think I've answered all the questions.
Mm-hmm.
Yes, I will stop sharing.
Yes. You can. All right, thank you very much for that.
Thank you.
Yeah, really good work. Really good to hear Python being used in that way. So next we have a talk on Coffea, Service X, and Python to rediscover the Higgs from Baidyanath and Gordon. So I will allow you to unmute.
Okay, you hear me okay?
Yes, loud and clear.
Yeah, and you need to also do the same. You have, okay, great.
Yes.
I hope I'm audible.
Yes.
All right.
Right. Whenever you're ready.
Sure.
Whenever ready, okay.
Let me share the screen.
Yep.
Is it visible?
Yes.
All right. Hi, everyone. I am Baidyanath Kundu from Manipal Institute of Technology. And along with me is Gordon Watts from University of Washington. Today, we are going to talk about using Python, Coffee, and Service X to rediscover the Higgs twice. So what Higgs we are talking about exactly? We are talking about the famous Higgs boson that was announced 9 years ago by both the experiments, ATLAS and CMS. And both of them released their data and the source code to reproduce the analysis. And today we are going to attempt the same. So we are going to attempt the same using ServiceX, FunkADL, and Coffee toolchain. So this is the pipeline that we are going to use. First of all, using a Jupyter notebook, we are going to send a query code to ServiceX. ServiceX takes note of which data set is required from CMS Open Data and takes it in. It then slims it down so as to fit the query code and saves the slimmed down data to the disk cache. Then the data is sent back to the Jupyter notebook or directly to Coffee, depending on whichever is more efficient. and then the analysis code is sent from Jupyter Notebook to Coffee. The Coffee runs the analysis code on the data using a local or Dask or FunkX runner, and then sends back the result. So this is the whole pipeline. So what's CERN Open Data? CERN Open Data is a data repository for the public LHC data. It has over 2 petabytes of data and thousands of data sets. This is an overview of ServiceX. ServiceX takes in the data set from various formats like XAOD, NanoAOD, flat and tuples, and then it takes in the user query and slims down the data and sends it back in form of data frames, awkward arrays, etc. Now Gordon will take you over the rest of the pipeline.
So Coffee is a lightweight processing framework and toolkit written in Python. It's built to process columnar data, but at the same time give you an event-wise view. The toolkit actually contains a lot of extremely useful utilities, paradigms, and approaches. But for the purposes of our talk, there are just a couple of things that features that we wanted to pull out. One is it's built to process files. It has distributed processing built into it, although we are only going to reference that in this talk. And it's got a very flexible data model, and you'll see that in evidence as we switch between columnar and event-wise views of the same columnar data. Next slide. We're going to look at 3 different notebooks in this talk. One is an introduction to FunkADL, ServiceX, and Coffee. The second is using the Atlas public data to remake the Atlas plot. And the third is to use the CMS data to remake the CMS discovery plot. There is, okay, I'll get back to that. First, the other thing that both of us wanted to mention is this is very much a team effort. This should not be seen as just the 2 of us doing this work. There are places where we've outright stolen code from other people's projects. We've given credit in the repository, but I just wanted to make sure that we acknowledged many of these folks. In particular, I want to mention that Mason, who is the author of the Uproot backend, is going to give the next talk, and he's really going to make the FunkADL language, which we'll see in a moment, sing in a way that we will not have time to discuss in this talk. Okay, next slide. It is possible to run this yourself. The tutorial is GitHub is linked at that top link, and that goes directly to the talks subdirectory, which has the 3 notebooks that we're going to show here. There are instructions for setting up in the repository at the very top level, but as you'll see, there's some very much beta software involved. We're happy to give out the ServiceX endpoints. We just didn't want to put them in the repository for all time. They're unofficial at the moment for accessing the open data. We're working towards production versions. Some of the integration with Coffee is beta, although all up on GitHub. And probably the most important point is it's not obvious to us that a certain open data portal can actually serve the data at the rate that ServiceX really wants to ingest it. And we'll make a few comments about that. And finally, unfortunately, Binder is not supported. And the reason is ServiceX for data download uses a non-standard port, and Binder only allows external access on port 80 for very reasonable for reasonable reasons. Okay, is that the last slide?
Yeah.
All right, so let's switch over to the notebooks. I wondered if I could ask the organizers if, could you stop screen sharing? I wonder if I asked the organizers, it looks like we started a little bit early. Does that mean that we have a little more time, or are we trying to keep things compressed?
I suppose I think we finished about 5 minutes early on the last talk, so we can give
go
that
to
extra 5 minutes to you.
I can go to 8:20 is what you're saying. Sorry, to 20 after the hour, I think. Okay, that sounds good. First, let me ask if I have increased the size of the font enough that everybody can see.
Yeah, we can see properly.
It looks good. Okay, fantastic. All right, so let's get started with our first notebook. This is going to be fun, but it's also going to be fast because, as you might imagine, looking for the Higgs is a relatively complex operation. The very first thing we wanted to do was to demonstrate the pieces of that data flow diagram that Ina showed earlier in the slides. So the first thing I have to do is set up my environment. And if you look carefully, you'll notice there's something that refers to the CMS run one data. The CMS released it as AODs, and there's something that refers to so-called an uproot data. Uproot data is a pseudonym for flat root files, and Atlas released its Higgs data as flat root files. So flat root files are perhaps conceptually the easiest to understand, so let's start with that. So the very first thing we need to do is we need to tell the system or service X where to go find the files. Let's just look at a single file. This is going to be a Higgs signal, 125 GeV Higgs decaying to ZZs, one of them off shell, and then to 4 leptons. All right, so all I did there was declare a source of data. I didn't actually do anything. So the next thing we're going to do is run the actual query. So this here is the important part. What we're going to do is run it against a live instance of service X. Right now, service X took this query, which is going to select lepton PTs. It spun up a series of containers on a Kubernetes cluster to ingest the data, and then it takes that data, the Atlas n-tuple, which, as you might imagine, holds many, many, many different columns of data, and selected out a column called lepton PT, turned it into a so-called, shipped the data back to us locally on my laptop here in my mother's, my family home where I grew up, where I am right now, and converted it to an awkward array. And at the very last line there, you'll see that we printed it out right here. Now, it's a standard awkward array, and you can see it's just a series of numbers, which are all of the lepton PTs, but they're stored in MEV because that's the way Atlas works. Now, one thing that's very important for this talk is most of the time we will not actually go out all the way to service X. By running that, it caches it locally. So if I rerun this, you'll notice it's instantaneous. Whoops, I should have printed out R again, I apologize. It's instantaneous. There were no indications it was going out to service X. And that is, of course, the role of this ignore cache. And this means, this is because some of the service X queries we have in here are running against terabytes of data. We cannot complete them in the time of this talk. Okay, so that was a call out to an actual, to the running service X instance. If this was a computer that had nothing on cache, every single one of these queries would go out to that service X instance. What's returned is a regular awkward array. As you can see, a lepton PT with one element per event. So it's got 164,000 or 165,000 events. We can plot it. I'm using the hist package, which is a very nice Python histogram package based around a core of C++ code and Boost histogram, which is a histogram in the famous Boost library. Looks exactly as you expect if you brought back the lepton PTs with no cuts. All right, it's really not the muon PTs, it's the lepton PT. All right, perfect. So what if we wanted to get back more than just the lepton PT? So let's get back the ADA as well. And you can see what the structure is. It's two columns, one of the left, the PT, and one of the eta. Simple enough, but much more interesting maybe is what if we only want to get central electrons? One of the advantages of Service X is that it's in a big cluster in a facility somewhere. It's all written in Python, by the way, but and it is near a very large data pipe. I am not. I'm at the end of an ADSL line. So what I'd really like to do is limit the amount of data that comes back to my laptop or into my analysis facility if I was running on an analysis facility. So here, let's take the leptons and let's cut any and only bring back the central leptons. That is the eta with less than 1.0. All right. So if we do that, again, notice the same number of events come back because we made the cut on leptons, not on events. So let's look at a plot now where we look at the the number of leptons as a function of PT. Again, I have you on track. It should be lepton. I apologize. So you'll notice we filled it twice. Once where we used all. So that's this line here. We're using the first result. And the second one here is where we used our cut, which if I, pardon me while I scroll just a little bit too much, we use our cut coming back. Look at that. That's an error. Okay, there we go. Okay, so we've done that, and you can see the effect of the cut. It dramatically reduced the number total of leptons that came back. All right, and we can, whoops, sorry. We can make, I had a new motherboard installed in this last night, so there may be some weird things that come up. You can make same plot of that data and just count the number of leptons in the data. You'll notice that from Atlas, it came back. Everything, when you make no cuts, comes back as 4 leptons. That's because the data is highly skimmed that they showed. They stored for open data. And you can see this skew down low when we make the cut on eta as many leptons get dropped because we've made such a tight central point. Okay, PyHEP is going to talk a little bit about doing the same thing, but doing it from CMS run 1 AOD files instead of the Atlas files.
Yeah, so you saw how Atlas was doing it. Now for CMS, there are few differences that you have to keep in mind. First of all, if you want to do it without Service X, you will have to install a old version of CMS SW. Now that version comes in a VM or a Docker, or you have to install the whole source along with dependencies, and it is a very complicated step. Second, the data in these files are row wise and not column wise, like in the case of AOD files, Atlas AOD files. And the third thing is that the data sets are very huge. It's like 7 TB for some of the data sets, and it takes about 30 minutes to run on Service X when they are working well. For your personal PC, I don't know how much it will take, and it will not, you will not be that patient, of course. So we will be using data from an earlier run, and that has been locally cached because that will take us a lot of time to run in our case too. So let's look at the query. It is the same query that we showed you for the Atlas side. The difference being we are using muons instead of leptons. So you can see at line number 2, we have used e.track muons. And that is one of the object that tells Service X that you are taking in a muon, but you are storing it in a track collection. If someone is familiar with CMSSW, they would know what I'm talking about. It's a special kind of collection for tracks, but since we are storing a muon, we also have to include the header files that pertain to muons to use the properties of muons. The second, after that, it's almost the same as Atlas side. Muon PT is taken out and is stored in mu PT, and then sent to the sent back from Service X. Again, if you see the number of events, it is different, but if you compare it with the cut on the eta, the number of events remains the same, because again, we are not working on the event level, we are working on the muon level. So the number of muons get cut off from the events, but the number of events remain the same. And finally, the histogram that you see, it is also skewed towards the lower side, as in the case of Atlas. So things to keep in mind when using CMS is that CMS stores all the muons, like in this case, all the muons or all the data. They do not clean it when storing it in open data, unlike Atlas does, because Atlas skims its AOD files because it's for educational purposes, and they don't place all of the data in open data, only the amount of data that is required. Now Gordon will take you through coffee.
Okay, so let's talk a little bit about coffee. We've got about 10 minutes left, so I'll make this a little quick. And part of the reason is because a lot of what you've seen before about how we get the data out of service X is just going to be repeated here. So what we have to do is bring together a query for service X, the analysis code, which sits in CoffeeA, and some sort of an execution policy, be it execute locally single-threaded, execute on DAS, or funcx, as was mentioned earlier. So this is the main way that we're using Coffee. So let's look at that structure. The very first thing we do is we create a query in service X. We'll call it selection atlas here. And all I've done is created this query. Nothing got executed at this particular moment. The second thing I've got to do is create a CoffeeA analysis. So this analysis is dirt simple. It's going to create a histogram. It's going to grab the leptons that come from the event, and then it's going to plot the leptons. So it's basically the exact same thing that was done before, but now we've done it in a processor. And the beauty is if our data set had 20 files, Coffee would automatically split up those 20 files, run this processor on each of those 20 files, and then coordinate combining the results, and then returning a single histogram to us, the user. All right, so now we have to define the data set for Coffee to run on. It's very good at running on multiple data sets, so it requires us to do a little bit of extra work. I'm not going to go into the details of that. Finally, we also need a bit of boilerplate, which links together the processor, which will do the analysis, the execution policy, we're going to use local execution for here, and the data sets all at once. Again, this will query service X, and it will grab something local. This is just an example of what the result looks like. And you can see it's got here PT is one of the results, which is a histogram. And we can make a plot of that, which should look, at least to my eye, it looks identical to the plot that we had earlier on the Atlas data. All right. You've seen the framework now. This last piece of the example is exactly how both the Atlas and the CMS Higgs examples are structured. So we're now going to go through very quickly the Atlas example. The Atlas is only a half a gigabyte, at least as a zip file, all of their flat root files. So it's actually not a lot of data. So this is interesting from the point of view of how the analysis is structured. It's not interesting in the point of view, I get, as a challenge, at least for distributed computing. That will come with the CMS one next. Okay, so the very first thing is we have to build a query. And one of the aspects of the Atlas analysis is we need to do a trigger selection. So all events have to be, we have to filter at the event level and select electrons or muons. The next thing we've got to do is we need to make different cuts for electrons and muons, but Atlas piled electrons and muons into the same set of branches. So what we're going to do is build a lepton object. It's like we're building a new event data model right here. We'll build a lepton object, separate it into electrons and muons, and then make the cuts. This step builds the electron object right here. And then here, notice we take electrons. This is how Atlas tells the difference between the electrons. There's something called the type ID. If you're familiar with particle physics, you'll know exactly what that's referring to. This is real data, not Monte Carlo, though, for those of you who get the inside reference there. So we separate into electrons and muons, and then we do a series of cuts. These cuts are pretty similar to each other, but you'll notice some differences. Like there's a different eta cut that has to do with detector geometry. It's a slightly different track isolation cut as well. All right, so this is us defining the query. Now, one thing to note is that at the upper level, when we combine the 4 leptons into the invariant mass to search for the Higgs, we don't actually need all of this data that we cut on. So for example, ET cone, that can stay at service X. No reason to bring that all the way back to the laptop here. So that's this final step where we declare the exact things that we want to bring local to the laptop. So we need the lepton, the electron and muon as separate things, along with some scale factors. All right, we finished defining the query. The next thing we have to do is define the analysis. I'm not going to go through this because most of this is going to be fairly, I don't know if it's sophisticated. To me, it was sophisticated when I wrote it, awkward array manipulations. So here, basically what we do is we do a final cut on the electrons and muons. We make an event mask, which checks that there are exactly 4 muons, or sorry, 4 leptons, which is what's required by the Atlas analysis. We then make a ordered pre-selection cut. And then after that, we have to look at the EE mu mu, the EE and the mu 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 channels separately. For those of you not familiar with the analysis, don't worry about it. It's so much. It's just some extra code that means we have to split this into 3 different sort of sub-analyses. But we combine them all, fill the histograms, and then return them to Coffee. So that's our Coffee process. All right, so let's create a data set again. I'm using it slightly more sophisticated because I want to run on lots of data sets. Here are all the data sets that we're going to run on eventually. And then here is the boilerplate code I mentioned before, which brings together the execution policy. It brings together the analysis to do the actual running. And then finally, it also brings together all of the data sets, which is just a little bit off screen right here. All right, so let's run on a local version of just the same original file that we've looked at for the lepton PT before. And now let's make a plot, and lo and behold, there's the Higgs separated out by channel. All right, great. Actually, let's ignore that. So now let's run on all of the data files. This will take a second because it's running in a single threaded mode. It'll take more than a second. So it's now got to process data from each one of those files and then pull them together into an overall plot. There we go. So it was a little nerve-wracking. This plot isn't interesting from the physics point of view because it's got everything all piled together, but you can see sort of what the overall plot looks like. Much more interesting is, say, let's look at the data, and look at that little Higgs bump along with the more Z-like bump. But of course, the real question is that signal where we expect it? We've already looked a little bit at that. So that signal is at 125. And then let's look at just the backgrounds. And you can see the background has no peak around 120, which means that that data plot is looking almost the way we would expect. All right, let's look at the CMS version of this analysis. Sorry, this was meant to be at the top. Take it away, Adinath.
Yeah, let me share my screen. Is it visible?
Yes, sorry. Yes.
All right, so just like as you saw it in Atlas, again, the steps are pretty similar. We just a couple of differences. Again, I am going to repeat that we are not going to be running it in real time. The total data that is required is 70 TB. We could only get about 43 TB running for this notebook when we ran it the last time. This is because we told you that it takes 30 minutes for 7 TB when it's good, but the problem is that the CERN open data and ServiceX collaboration might not be working right now. So that's why we could only get about 43 TB. And ServiceX return locally is only 10 GB. So this is, again, we first set up all the libraries that we are going to use, and then we define the base query. So this is the line number. So this part, you might see it's written dummy. That's because we will put in the data sets later when we are running on all the data sets. So this is taking out all the muons, electrons, and the vertex position. So this might not be what you saw in the Atlas side, but this has a particular use on the CMS side. So when we are doing the cut on the muons and electrons to get the good muons and the good electrons, then you can see where it is used. It's used here, the I.P, to get the dxy of the global track of the muons. So this is the whole query that is run so that we could get the good muons. And like we said before, the number of cuts have to be more in CMS side because the data set is more and it is not cleaned as in the case of Atlas. So similar, the muon and electron have almost similar cuts, except for a few, but even they are similar on the base level. Then we take out all the properties that we require for muons and electrons. So PT, phi, eta, energy and charge. And then we go on to the analysis. So this is the analysis code. This is where we do the cuts and get the good muons. And from here starts Brian Cruz's code that we directly copy pasted into the notebook. So this whole code from here to up till here, sorry, not that, up till here is the whole code from Brian's notebook. And after that, we do some more calculation, and then finally we plot the Monte Carlo file. So this is just to run the analysis on the data set that we have. And this is the plot that we get from one of the Monte Carlo files. The mass is centered at 125 GeV, where we expect to find the Higgs. And this is not that interesting. When we run it on all the Monte Carlo and data files, then we get the bigger plot. This is where the Z is supposed to be 91 GeV and the Higgs is at 125 GeV. This is again Monte Carlo data set. And this is the whole plot of everything stacked on one at the top of another. After that, we were running the data set files, and you could see that Higgs is coming up, but it's not complete, so we can't see a clear plot as in the case of Atlas. But this is a work in progress, and you can see that the Higgs has already started appearing. So we plotted out the different signals, like this is the signal for Higgs only from the Monte Carlo dataset. And this is again, like we said, 125 GeV centered signal. We also plotted the background only so that we can see that it doesn't contain the Higgs. And like we said, if we subtract the background from the whole signal, we will get the Higgs plot that we showed above. So this is all the all the different particles in a plot except the Higgs. This is for again for the Monte Carlo dataset. And that's it for our presentation. We will take questions now.
Excellent, thank you. So we do have some questions over on the Slido. If one of you would like to bring up the
Sure. Could you send the link? I do not have a link.
Sure. Ben has quicker fingers than I do. He has just posted it in the Zoom chat.
There we are. Thank you. And let me share. All right. The interface does not look the same. Okay, I just got. Can you hear me?
Yeah, we can hear you.
Briefly cut out, but
A message, I think. All right, I just got a Zoom quit unexpectedly.
Okay, let me share the
I
screen
can
instead.
share the.
I can share it. Is it visible?
Yes, that's visible.
Okay, how much prep was needed for this talk, or rather how much was real time, particularly the multi-sample Higgs mass plot? So after ServiceX was built up, we took about 3 or 4 days, like this week basically, to complete this talk. That was mostly because of the CMS data taking a lot of time, and even then we couldn't finish. But the Atlas data would have taken much less, just the code and stuff in that part.
So sorry about that. My Zoom client crashed for whatever reason. I measured the Atlas time from start to finish, and it was less than an hour to fetch it all from CERN EOS. Biden is completely right about the CMS data set. One thing we observed is the first couple of times we ran on the 10 terabyte subsamples, it took us it would take us about 30 minutes, 45 minutes. But I think we may have triggered some sort of rate limit, because by the end, the amount of data that we were getting back from the CERN open data instance was a trickle, and it slowed ServiceX way down. This is something that we'll investigate, but we don't fully understand where that slowdown is coming from yet.
Okay, so the next question is, what does the async keyword do? This is the first time I have seen it. So async keywords is used to run asynchronous function, basically functions that are not that can be run in parallel, and await keyword is used to make that function run in synchronous manner, and so that they are run in the way that we normally run functions, basically.
Why don't
Do
I
you have
take
something to add?
Oh, no, I was going to say the top question that just got upvoted at the very top of the screen, it shifted. So let me take that one. Who provides the computing resources on the ServiceX side? So we're running on a semi-test production cluster at University of Colorado. It's the so-called River cluster. It's part of IRIS-HEP. This is a large National Science Foundation software institute in the United States, and it has some computing resources. I believe, I may be getting this wrong, I believe that cluster is of order 1,000 cores and has a significant amount of disk space associated with it. But this cluster was only using, these instances were only allowed to use up to 200 cores at once. But CERN Open Data was never able to supply us with enough data to actually use 200 at once. So the system never expanded. I think the highest I ever saw it was 18 cores were being used at once to process the open data for those 30 and 45-minute runs. We could have used more for a shorter amount of time if we'd been able to source the data. Okay. You want to do the next one? Oh, sorry.
I think we might move the rest of these onto Slack, and do encourage you to answer them on there. We will move on though.
Thank you for having us, and it was a great time.
Thank you for the talk.
Thank you.
Next, we have Mason, who is giving a talk that dovetails quite nicely, focusing more just on the FuncADL side. So, if you could unmute and.
Let's see. Oh, okay. Yeah, there we go. Okay, let me share the screen. Should work.
If you could maybe zoom in a little bit.
Yeah.
Is
that good?
That's a bit better.
Okay. Yeah, so let's see, I believe I put my GitHub repository on the agenda now. So I'll talk about FuncADL. I have this notebook, which I think can run on Binder, but I was not organized enough to get it all prepared on there beforehand. But yeah, so that, as was already said, this is really focusing on getting into some of the nitty-gritty details of the language that we saw that goes into a lot of the work that Gordon and I and by Jan have been doing. And right, so this FuncADL is this functional analysis description language. I talked about this at CHEP or VCHEP in the past couple of months, so you may have already heard about it a bit if you were at that. So I copied some of the motivation basically from those slides. There's kind of two main motivations, kind of two camps that are motivating FuncADL. One is query languages coming from database management systems, and the other is functional languages. So query languages and databases have these advantages in terms of avoiding data redundancy, where the idea is that you just query your data source that's stored in the database, and there's no connection between the query that you're writing and how and where the data is actually stored. So it can be in some central place, like running in ServiceX at some cluster. And then also, this is closely related to data independence. So this is really more focused on the idea that the code or the queries are not connected to the schema, the physical and logical schema of the data. The interface is completely separated. The language that you use to access the data is not connected to the format or location. This is a key aspect of languages like SQL. And then for functional languages, so this is the functional programming paradigm, has a lot of advantages for analysis, data analysis. It's a type of declarative programming, so it's not procedural. You don't focus on writing how you loop over and iterate over every part of the data. It's stateless, or at least that's the purest functional programming is stateless, where there's no side effects. You don't have global variables and things that are carried around, and it's very easy to make functional languages. They're kind of intrinsically lazy, because everything is in terms of functions are first-class citizens. So functions are really passed around rather than values or the evaluated functions. It's just the functions themselves. And this little thing that's missing there. So these concepts help insulate in a couple ways: the analysis code from the data storage format and location, and also insulate each part of your code from other parts of the code, so more modular. Okay, and as I said, FuncADL is borrowing from these concepts, the functional data query language, using Python as a host language, and it's based on quite a bit on LINQ, which is a collection of features that are built into C#. So for this notebook, okay, so I just set up some things. I use matplotlib. Let's see, I think everything is filled here. So I'll just, yeah, I'll restart and clear the output. So yeah, I use matplotlib just as the basic plots in here. And so what I'll be using for FuncADL is I'll be using a particular backend. So FuncADL is the language, the interface, the user-facing interface, and then your query that you write in that interface gets run by a backend that can translate into all the details of how to run that query, and that can depend on what the format is or where the data is. So this is the level of separation between the interface and the actual execution. So here I'm using the uproot backend. You already heard about there's the CMS like open data backend, and there's an XAOD backend. I've focused, most of my work has been on the uproot backend. So here I say from FuncADL uproot, which is the package for the uproot backend, I import uproot dataset. So this is explicitly saying that I want to use the uproot backend, which is quite powerful. It can run on any ntuple that doesn't require special like framework software to interpret. So any flat ntuple. So I'll import that, and then the data set that I'm using here it's in nanoAOD format. So here I'm actually using the full file that's on XRD, and it's been converted from CMS open data. So I'm using this root path here. In the binder version, this file is fairly large. It's like 50 gigabytes or something, not huge. But for faster and easier running and easier use on binder, I wasn't sure if XRD worked through binder. I just copied a small subset of this file. So if you open the GitHub repository, this will just be a file that's a small file that's sitting in the repository that just has the first 1,000 events from this sample. So I'm going to try to see if I can run on the full sample during the talk here. So okay, now I have this data set. So in the rest of the notebook, the strategy that I'm going to use here is basically I'm going to act like this is a tutorial on FuncADL. So I'll kind of introduce new concepts gradually, and then once we have some concepts, then start applying them to these ADL functionality benchmarks that were developed by the HEP Software Foundation and IRIS-HEP to demonstrate functionality, the core functionality between different analysis description languages. So we'll see those come up as we pick up the tools necessary. So the first thing, the most important thing to be able to understand how to write something in FuncADL is that almost everything is treated as a sequence of some generic elements. So for example, an array is a sequence of rows. So an array can easily be looked at, or at least an array that has more than one dimension. And it's not just a 1D array. So usually we at least have events, and then in HEP we usually have events and then things within that event. So there's usually at least 2 dimensions. So the array of events is a sequence of rows, each row corresponding to an event. So this data set object that I have here that I call DS, this uproot data set, to FuncADL, this is just a sequence of event objects. And so an event object is effectively a dictionary or a record containing all of the properties of the event. And these values can either be scalar primitive types like ints or floats, or they can be sequences themselves of other primitives, or sequences of sequences, and so on. So almost all FuncADL query operators expect to act on a sequence. So the most common type of operator is select. That's kind of the most basic one. So select is a projection operator. It transforms each element of a sequence that it's given according to some predicate lambda function. and the output will be the sequence of all the transformed elements. So it's basically a map, like the built-in Python function map, but it's just more generic, because you can do it at different nesting levels. So for each one of these operators, I kind of give I say like a visual demonstration of semi-pseudocode what is happening with each operator. So here, if we have this sequence of like 1, 2, 3, and we apply a select operator on it, here the projection function or the mapping function is just take each element X and add 1 to it. So it turns this sequence left into the sequence on the right. It just adds 1 to each element. And this is all we need for the first benchmark task. So the first one is, there are 8 of them. I think I put the link up here, yeah. The first one is, I won't go through all of them, but the first one is to plot the missing ET of all events. So met is stored in a branch that's just called met PT, missing ET. And so the query, it looks like this, and we can assign it to a variable. This is just this pure funcadl query. It's this dataset dot select, and then we use this function to map each event object to this value within the event, the met PT. And so I can evaluate that cell, and it immediately returns, because we didn't actually do anything with the data yet. funcadl uses delayed execution, as was mentioned in the last talk. So the value won't be calculated until we ask for the value by saying dot value. So then in the next cell, if I execute this, now it's taking a second, it's executing. I put the time on here. So it takes a few seconds to pull out all of the missing ET values from all the, I forget, like 15 million events or something like that. In fact, well, yeah, okay, we'll get to other operators later. But so now I have the actual, the array of net. And so now I can examine this. It's just an awkward array of all of these values, and all of the values are in GEV. There are 53 million events. And then I can plot it, which is what the task says to plot a histogram of all of the missing ET variables across events. So that'll take a second. There we go. Okay, wow. Okay, if you zoom in, the plot gets huge. But here's a histogram of the missing ET for all events. Now, okay, so the next operator is select many. So this is an operator that it starts by doing the exact same thing as select, but after it applies the function, the mapping function, it assumes that the output for each element will be a sequence itself. And then after it does this for all of the elements, it will concatenate all of the resulting sequences. So again, visually, it looks like this. If I take this little sequence here, apply a select many, where I just transform each element into a sequence of 1 minus the element and then 1 plus the element, then I'll get 6 elements out, because it turned it into this intermediate sequence, a sequence for each element, and then it just concatenated them together. And normally this operator is used when the elements were already sequences. So things like jets and electrons and muons, we already have a sequence of those in the event. So we can actually use select many just to flatten the array without doing anything else, if we just have a trivial mapping function for each element to itself. So this will just flatten like this jagged array into a 1D array. And so usually we're using select many on something like jets. So here the next task is to plot the PT of all jets. So I use select many on the jet PT to do this. And so it'll take probably a few seconds to execute. Now, one thing that you can see is that you could also just use select for this. There's nothing wrong about about just using select, but if you do this, you will get a jagged array out because it won't get flattened. So we could have used select for this task, but then you'd have to manually flatten it afterwards in order to make a histogram. Okay, so I'll let them keep running in the background. I think it takes like 20, 30 seconds or something. And I'll go back up when they finish. If you're running on the, in fact, I think I have the, there we go. Yeah, so it gives this flattened array. If I use select instead, I get a jagged array. You can see there's sequence, or 1D arrays within this longer array. You get one array per event. So you have to flatten this. And so, okay, I just take the flattened version that from select many and make a histogram of JetPT. Okay. So we can select and select many. You can filter out event properties, columns, basically branches that you aren't interested in. But another thing that we pretty much always want to do is filter out certain elements of sequences, like certain events or certain jets. You need to discard elements. So this is done with where. Where applies a function that will output a Boolean value for each element, and where will just discard any element if the function returned false. So like here, if you have 1, -2, 3, if you apply a filter for elements greater than 0, it'll filter out -2. You'll just get the ones that pass this selection. And then another important operator is zip. So if we're not just dealing with scalar values per event, so like met is just one value per event. If you're dealing with something like jets have many properties. So there are many jets within the event, and then each jet has several different properties. So we need to wrap together the properties that correspond to the same physical object, like physics object. So if we make a cut on PT, then we're also filtering all of the other jet properties at the same time. And so zip does this. It's very similar to like awkward.zip. There's a version of awkward.zip that it's using in the back end. So if you have a sequence like this that has 2 sequences within it, if you zip it, it's basically a transpose of the matrix. It'll match the first element of the first sequence to the first element of the second sequence, so 1 and 2, and then the second elements 3 and 4, and then the third elements 5 and 6. And it's often done with the dictionary, so because it's easier to keep track of all of the properties. So if you have, property A in some branch and property B in some branch, and then you zip them, then you'll turn this into arrays of records, basically, array of dictionaries. And then so like the next task requires doing this. So it says plot the PT of jets with eta less than, absolute value of eta less than 1. So you need to make a cut on eta, but also propagate that cut to the PT values. So here I use a select many so that it will flatten. And then I can make a dictionary or a record for each jet of the PT and the eta. So these are both arrays. Jet PT is or a sequence, and jet eta is an array. Then I zip them together, and then I say where the absolute value of eta is less than 1. And no, you can use built-in functions, built-in Python functions like ABS. And then I select the jet PT from those jets. And so then I can execute that. And this will give the filtered jet PT values based on eta. Okay, and then that'll take a little bit to execute. Okay, so the next operator, another example of one is count. So if we need to filter based on a discrete number of objects, like a certain number of jets, then you need an operator like count that takes a sequence and just returns a scalar. So it's a reduction operation. So the count just gets the length of the sequence. So if there's an array with 3 elements, it'll output 3. So then the next one here says plot the missing ET of events that have at least 2 jets with PT greater than 40 GeV. And so I do a where to filter the events based on, so inside the where condition for an event, I look at jet PT, and then I look at the jet PTs where the PT is greater than 40, and then count the number of elements that pass this, the number of jets that pass this. And that's, if it's greater than or equal to 2, then that event passes this filter and you select the Met PT, the Met value. Okay, and okay, that's still executing, but they will work. If you run on the yeah, if you replace it with the, if you're running on binder, it should be much faster because it's just 1,000 events. Let's see, so I've, yeah, okay, so maybe I'll bring up the Slido if I have it somewhere. Just yes, okay, because I see I've got, okay, like 9 minutes left, so I'll start looking at questions. If I'm not going to get through all of them, I haven't, this is still in progress because I haven't finished implementing all of them. The last 3, I believe, are I have a sketch of what they'll look like, but they'll have to wait for future versions of the uproot backend. So I'll look at the questions. Exactly, yeah, so somebody said
if you could screen share the questions.
Yes. Yeah, maybe I can, yeah, that'll work. Okay, so yeah, somebody said that this looked, and the previous presentation looks like our data frame. Yes, it is very much like our data frame. It's somebody, so that they're saying not totally Pythonic. I guess I don't know if I necessarily agree that it's not Pythonic. It is definitely very similar to our data frame. Our data frame has a lot of the same motivations. One of the main thrusts for FuncADL is not having it tied to root. It's basically, you know, so it's in Python and it's separated from, it doesn't, you know, this is using uproot. It's not, FuncADL itself, kind of the general language, isn't tied to any backend. So I guess Pythonic is, you know, it's a subjective thing. It's functional. It's more of a functional programming thing, and Python is not the most functional language, but it certainly you can put in some of the aspects of functional programming. What is the benefit of using FuncADL compared to vanilla uproot / awkward? So yeah, I actually have a version of these of the benchmark tasks where I implemented it in just uproot and awkward. That's on my GitHub profile somewhere. It's like uproot benchmarks. So you certainly can do it. The benefit here, there's a few. So there are some kind of, I think the main benefits come when you have to deal with more dimensions, like more axes. So when you start dealing with sequences of sequences of sequences and so on, this notation based on queries is, I think it's easier to keep track of kind of which dimension you're in. With awkward, if you're manipulating arrays with awkward, you have to kind of manually in your head keep track of which axis you're on, whereas FuncADL keeps track of it for you based on where you are in the query. So that's one of the benefits. The other big one is that you don't have to use, FuncADL is not tied to uproot either, just like it's not tied to root. You can make a backend that anything that can basically perform these operations, these query operators can be used. So like there was a early version of an R data frame backend for FuncADL that still exists somewhere. And then we already saw the XAOD and CMS backends. So you can use the same interface for many different types of data formats and also different backends. So that's, yeah, I would say those are two probably the biggest ones. It's also kind of ties you more to like the functional programming and declarative way. With uproot and awkward, you can still, it's still pretty easy to make it more, you know, procedural, and you can do loops with, you know, with uproot and awkward, although it's not a good idea generally. Okay, so let's see, why did we use a lambda function? So that's just part of the, it's just part of the language, because these operators expect functions. So this is the functional programming part of it. The fact that these operators, the arguments to these operators are generally functions. So you need to pass it. It's like I was saying, like map in Python is an example of a built-in that expects a lambda. I mean, I guess it doesn't have to be a lambda function, but it's usually easier to read if it's a lambda function that's just right there in the line. So it's just a way of, trying to stick to functional programming, the paradigm, and making it more declarative, because everything is contained within the query. You're kind of like, by restricting it more, by requiring that the lambda function is in the query, it kind of limits how nasty it can get. I mean, it can still get very long, but it's not like you have to go look at some library, 3 levels deep to see what function you're using. Let's see, usage of where, for example, is different from panda style. Is that for some special reason, or would it be viable to try a more widely known API? Yeah, so this is just, I think, it's just a convention, and the convention that's followed here is link. So it's based on the link API of where. So I don't think that would change. Generally, if there's an operator that already exists and there's not an in link, and there's not an obvious reason to diverge from that, we usually use the link syntax. Stylistically, using camel case feels quite root versus snake casting operators, which would be more Python. That's fair. Okay, I mean, this comes from link. This is the convention on capitalization is entirely from link. So yeah, I guess you could argue that's not entirely Pythonic. Is the aspirations to expand the supported queries to match link more closely, joins and group by? Okay, well, that's something you'd also have to, talk to Gordon, other people who maintain other backends. I think certainly, like, I've already started implementing more operators that are fairly directly from link, like order by. Joins and group by, maybe. I would say definitely that the idea is to expand to more link operators if they seem like they're useful for HEP and data analysis tasks. And I'm starting to see which ones are more useful from like going through these benchmarks. Maybe in the last few minutes, I'll just go through because I still don't see any more questions. I'll just go through this one here, because one of the most important updates since VCHEP is, well, the second thing here. Okay, so one thing that I implemented was choose, which is, so just dealing with combinatorics is always a pain, and it's a common thing with HEP. So it's a thing that it's like n choose k, like this kind of combination thing where you need to take like 3 jets, like any combination of 3 jets. You don't want to repeat them within each combination, and you only want the unique combinations. So this operator helps with that, because it's possible to do it without it, but it's a huge pain. It's so much easier to do this really common thing with an operator like this. I actually forgot to put the number here. This should be choose 2, because it takes pairs. So this takes all unique pairs of elements. And then the important update that is in the release candidates for the next version of FuncADL is that I've added the use of vector to deal with 4 vectors. So I have this function in the uproot backend. In other backends, it doesn't necessarily make sense to have something like 2 for-momenta, because for-momentum objects already exist, like T-Lorentz vector already exists in root. But in uproot, in n-tuples, usually like the components of a 4 vector are in different branches. So 2 for-momenta just creates the 4 vector object with using the vector library. And so this is something that I've probably the most interesting update that I've done recently, where something like this, where you need to plot the missing ET of some kind of pair of things here, opposite charge muon pairs with invariant mass. So you need to calculate the invariant mass. So here, let's see, I see I have like 1 minute left. I pick out the muon charge and 4 vector, I call P4 here, and then I choose pairs of them, and then I look at where the charge is, where they have opposite sign charge, and then I the nice thing is with vector, I can just add these 4 vectors together and say dot mass. And then I can say mass is between 60 GeV and 120 GeV. And then if there's at least one of those, then I pick out the net. That's what the task is. So then this now works. So it eventually will catch up. I see some of the other cells have executed, but this works now. And then I say at the end here, just there are some unfinished tasks. I've got some things sketched in, but they don't work yet. But hopefully in the next version of the uproot backend. Okay.
All right, thank you very much for that. We will move on to Giles next, who will be on Lumen. So we have, sorry.
Can you hear me okay?
Yes, you are.
Excellent. And you can see the screen.
Yes, we can see and hear you.
Yeah, excellent. Okay, so good afternoon, good morning perhaps, everyone. So my name's Giles, I'm the developer for Lumen. Lumen is a high-level wrapper to PyTorch. Basically, it's been specifically designed for use in high-energy physics. So just to quickly motivate why Lumen. So for the last few years, there's been a general trend in physics analyses to move away from implementing a BDT in TMVA in root to doing something a bit more advanced, perhaps a deep neural network in Keras. However, once you move away from root, from TMVA, there's actually quite a high barrier of entry in order to actually get something running, both in terms of the data, in terms of the software, and also in terms of the literature that has to be read in order to achieve as good performance as possible. So the majority of the time is spent getting something working. And due to analysis deadlines, there may not be time in order to get the best performance you possibly could. Similarly, hardware is going to be a limitation. Maybe you only have your laptop CPU to run on. But then when you come to internal reviews, they're going to sort of demand the highest level of analysis sensitivity. So where Lumen comes in is I aim to try and help ease physicists into getting a DNN running in their analysis. So as I mentioned, it's a PyTorch wrapper, but there's a few high-energy physics specific methods and classes in terms of helper functions, losses, and also architectures that are unique to our domain. And it's also a central package for many sort of state-of-the-art methods that you can use to achieve better performance. And this hopefully lowers the barrier of entry into actually applying these methods. Now, I actually put out a paper last year where I showed that using these methods really can help achieve very good performance in typical high-energy physics tasks in a short time on non-dedicated hardware. So even if you just have a laptop CPU, you can still use these methods. So to try and demonstrate this, we're going to use the Lumen package to attempt the HiggsML Kaggle challenge. This was run back in 2016, before that, 2014, 2013. Attracted a lot of interest from the community. The challenge itself involves a signal background binary classification. So the signal here is Higgs to Dieterle, and there's a few background processes as well. And this is based on Atlas 13TV Monte Carlo data. Now, the process of developing the classifier involves several stages, some of which are common to any sort of application of machine learning, and others are going to be specific to Lumen. So we're going to import the data from CSV formats. We're then going to pre-process it. We're then going to train an ensemble, multiple neural networks using quite an advanced architecture and training scheme. And then we're going to apply the ensemble to the validation data and also to the testing data as well. And then we're also going to look at how we can interpret it to understand what the model learns. This tutorial that I'm showing here is a cut down version of the full tutorial that's included in Lumen. There's a link to those there. If you want to follow along to this version, in the agenda, there's a link to run on Google Colab. That, I think, would be what I'd recommend, just because it starts with an environment with everything installed, GPU. If you select a GPU runtime instance, it'll be slightly quicker. So the first cell, this will just grab the data from the CERN Open Data Portal, and then we can pip install Lumen, and that'll grab the latest version. So I'm just going to start here because I already have the data in the model and in Lumen. Now importing the data, we're reading CSV into a pandas data frame. We have a few features. So the data set, as I said, it's Higgs to Ditow signal, and then several background processes. In terms of objects in the event, we have a hadronic tau jet, plus either an electron or a muon, and then up to 2 jets, if they're present, ordered by PT. And they have a default value of -999 if they're missing. And then feature-wise, we've got low-level information. So these are the PT to phi, the three momenta of the objects in the event. These are our primary features, prime. And then we also have a few derived features, high-level features such as angles or mass hypotheses that have also been computed. And our aim is to maximize the signal significance computed using the approximate median significance. So basically, we're going to develop a binary classifier, apply it to our data, apply a threshold, and select all the events that pass the threshold on the prediction, and treat those as signal. Now, of course, there's going to be some background in there as well, and that is what's going to determine the approximate median significance. There's in the data set that we get, there's also the public and private data that we use to evaluate the score in Kaggle, which can select out the public data. If we want to plot out a few of those features, there's this plot feat method in Lumen. This allows us to quite quickly plot out weighted kernel density estimates, signal background. We can also compute the mean and standard deviation of them as well. Now, pre-processing, this is something that you want to do whenever you're working with neural networks. But specific to high energy physics, we have this proc event method. What this is going to do is it's going to convert all the PT to phi vectors into Cartesian coordinates, so px, py, pz. Note that we're not actually specifying what the vectors are. It's automatically extracting them out from their names. So they're like leading jet underscore PT. That's picking up and identifying it as one of the components of the vector. We're also replacing the default values of -999 with nans, basically so they don't spoil our calculation of the standard for the during the standardization and the normalization of the inputs. For quick access, we're also grabbing the continuous inputs for our data, and we're also treating the number of jets in the event as a categorical feature. Eventually, we're going to spit out a validation set. We want that to be as close as possible to our training data and our testing data. So this stratification key is going to match or generate a unique ID in terms of the class and also the number of jets in the event. And then we can do a train test split, taking in that stratification key. There's a few features that contain nans. When we actually start working with the data, these are automatically going to be turned into zeros. So we can just ignore those for now. And then we'll split out a 20% validation data according to our stratification key. The final processing, so for the continuous inputs, we're going to standardize and normalize them. There's this fit input pipe method in Lumen that does this and returns a scikit-learn pipeline. So all the transformations are contained within the same object. So we can just do, we can fit it on the training data, and then we can use it to transform the training data, the validation data, and the testing data all separately. We don't need to do it here, but if our categorical features contained like strings or weren't starting at 0 and incrementing in ones, this propcats would transform the categorical feature into something that starts at 0 and increments in ones. And then it also returns this map here as well. And also, we have an imbalance of signal and background in the data. So we're going to change the weights of the data, and we're going to renormalize them so that the sum of signal and the sum of background are all ones. Note that we're actually taking a copy of the original data, of the original weights of the data, because we also then want to compute the approximate median significance that requires the normalization from the luminosity and the cross section. So having transformed our data, this is, it's kind of similar to what you would do for any machine learning application, except we've used a few of the unique methods in Lumen to reach this point. Now, though, we're going to transform it into a fold file, which is one of the core data structures that's unique to Lumen. This is an HDF5 file on the disk, however, contains several folds of the data. These are subsamples of the full data set, designed to be as similar to one another as possible. The advantage of this is, well, there's a few advantages. One is that you can load the entire of a fold into memory at once. If you have a very low amount of memory, you can just increase the number of folds that you split your data into. You can then identify certain fold indices to only be used for training, only be used for validation, or as we're going to do, we're going to train an ensemble of models using k-fold cross-validation. Some of the methods in Lumen are designed to treat each fold independently and then compute an average of some metric or some value over the entire data set, and also an uncertainty based on the standard deviation across the folds. There's a few other advantages there, but I won't go through them. So this df to fold file helper method, it's just going to split out our entire data set into 10, in this case, 10 even folds. Having done that, we now want to have still have access to the data. So these fold yielder classes what provide us access methods to the data on the disk. Specifically, though, we're going to use this HEP org fold yielder, which inherits from the base fold yielder. This will apply data augmentation to the data whenever we load it from disk. If you consider the Atlas detector, it has a cylindrical symmetry to it. We're colliding particles head-on, so we expect that events are going to have a symmetry to them. And we can actually exploit this symmetry in order to generate effectively new data that still has the same class. So if we have our event consisting of 4 vectors, we're free to rotate this event in the azimuthal angle in phi. We can also reflect it in the transverse plane, and we can also reflect it in the longitudinal plane, and still end up with a valid event of the same class, the same generator weight. However, to the neural network, it's going to have a completely different set of inputs. We can apply this during training time through the use of random flipping and random rotations. And we can apply it at testing time by, in this case, it's going to rotate the data twice. And for each rotation, it's going to do both flips in the y-axis and both flips in the z-axis. So a total of 8 transformations per data point. And then when we predict on these, we're going to generate a unique prediction per augmented event, and then just take the average of them. So this is yeah, a slightly more generalizing approach to prediction. We can see this in action. So here we're going to ask for training data from the same event, and hopefully that shows up okay. Basically, the same event here is just being rotated in phi, flipped in z and x, z and y even. But then when we ask for testing data, it's now going to move through all the 8 possible combinations of the event, or positions of the event, for 2 fixed rotations of the event. So now we have our data, we now want to construct a model. Now, in Lumen, rather than building a model and then training it, we instead have this idea that training 3 models, training 10 models should be no more difficult than just training a single model. So in order to allow this, we instead define how a model should be built and how a model should be trained. And then we pass these definitions to a method, to a function, and just say, okay, train n models. And then that'll just start, training, building the models itself, training them, saving them, and then moving on to the next model. So this model builder class takes in arguments for the network, for the loss, for the optimizer, for the inputs, and for the outputs. And then you can use it to generate networks on demand. A network in Lumen consists of 3 distinct modules. There's the head module, and the job of this is to take in whatever data you're working with and flatten it out into a vector, a flat vector by batch of hidden states of representation of the inputs. So if you're working, in our case, we're already working with flat data. So all this is going to do is take our categorical feature and learn an entity embedding, which is a matrix representation of the categorical feature that's a bit more efficient than using a one-hot encoding scheme. If instead we were working with image data or graph data, then instead the head would consist of a convolutional network or a graph network. This in the end would spit out a flat representation of the data. We then feed that into the body of the network. This consists of just hidden layers stacked one after the other. And then finally, the tail of the network is going to finally downscale the output of the network to match the required number of targets, the required number of outputs, and also put our final activation function there as well. Now, there's defaults already in Lumen. We can safely work with the defaults for our case. If you're working with something more advanced, then maybe you want to specify exactly what class to use for the head or for the body. In our case, as I say, we can stick with the defaults, but we can also still need to provide a few arguments. We can either provide these as a dictionary or create the class ourselves and then pass it to the model builder for each of the head, body, and the tail of the network. So in our case, we're going to change the body a bit. So we're going to use a swish activation function. Each of the hidden layers is going to be of width 32. We're going to have 6 of them in total. And these are going to be densely connected. So the output of every hidden layer is going to be concatenated with the input to that layer. This means that you never lose access to previous representations of the data. And then when you're back propagating the loss, you also have a more direct connection of the gradient to each of the layers. So you get this, I think it's called deep supervision effect going on there during the training. We also have this classification objective. This objective, so there's classification, multi-classification, multi-label classification, and regression. These are going to choose better defaults when instantiating the model builder. So note here that we're not specifying the output activation of the tail or what loss we should be using. Instead, it's going to pick up on the objective and say, okay, it's classification. So let's use a sigmoid on the output, and let's use binary cross entropy as the loss. So we define how the model should be built, and then we can create a model. This model class, includes the network, but then also a few help methods to train it, to predict with it, to load and save, etc. And when we print that out to get the representation of it, we get our feature names. All the features that are being used here are named. So there's a map inside the model, if you actually dig into it, that maps the output indices to the original inputs if they are distinguishable. So you can build up quite for the body, for example, you could have different sections of the body that only act on certain inputs. In our case, we're just feeding everything into the body. We also have our categorical feature here. And then in the network, we have the head. This is just going to learn an embedding matrix for the categorical feature, pass all the continuous input features straight through into the body. So we have our 6 hidden layers here, our switch activation. And then these are going into the tail, which is just single output with a sigmoid. Using the Adam optimizer, and the loss here, even though we didn't specify it, it's going to be using binary cross entropy. Now, one of the advantages here of Lumen is that the default PyTorch losses don't take weights when you're computing the loss. Instead, you have to specify the loss when the loss class is initialized. Now, in high-energy physics, the weights are changing all the time, quite substantially, event to event. So in the optimization loop of Lumen, it's going in manually changing the weights to the current weights in the batch. So that way you avoid having to re-initialize the loss at each time. Now for training, I'm just going to set this running. One of the most important hyperparameters is the learning rate. And rather than having to scan across a range of learning rates, do multiple trainings to pick out the best one, instead we're going to use this learning rate rangefinder test from Smith 2015. This runs across a range of learning rates, just doing a set of data. And it's going to start off at very low learning rates, move to very high learning rates, and then at the end we can plot out the loss as a function of the learning rate. And the idea being that the best learning rate to train with is the learning rate at which the loss is still decreasing. Now this is actually moved across all 10 folds of our data, starting from scratch each time. So you get the median prediction and then also the standard deviation across all of the 10 folds. Now from this, possibly 1e-3 is a good learning rate to train with. Here the learning rate is still decreasing, but after that it starts to stall, and then eventually the network diverges, the learning rate is too high. However, we're going to try and achieve super convergence here during training. So we're going to use a one-cycle learning rate schedule. This starts off at a very low learning rate, quickly ramps up to a very high learning rate, and then gradually ramps down to much lower learning rates. And it balances the high learning rates by decreasing the momentum in the optimizer. So we can actually handle much larger learning rates. So for this, we're actually going to use 1e-2. I'm just going to set this running whilst I talk about the rest.
I would just say you've got just over 5 minutes left, and we have a few questions over on the Slido. If you'd
right,
like
I'll try and speed up then. Okay, so yeah, there's a callback that implements the one-cycle learning rate. There's also a callback that allows us to compute the approximate median significance after every epoch. Now, during training of Lumen, you get this nice real-time plot that's showing the loss as a function of training epoch. For the training and validation, and then for the metric, this is also being computed at the end of each epoch. We can see how quickly the loss is changing per epoch, and also the ratio of training to validation. Now, at the end of training a model, it's automatically going to pick out the best model according to the loss and treat that as the final model of the training. We could instead pick out the best model using the AMS. However, that fluctuates significantly. So what we've done is we've said main metric equals false, which means it's going to automatically concentrate on using the loss to pick out the best model. Now, here we're training 3 models. It's going to use, or it's using here, the 0th fold of the data as the validation data, and then the rest of the folds for training. Now, for the second model, it's going to use the first fold for validation. It's going to keep on doing that such that you get this sort of k-fold style cross-validation for training the ensembles. We could specify to train more models than we have folds, in which case it's just going to loop back round and start at 0 again. So whilst this finishes off, I'm going to look at some of the questions. Maybe move that down here. Can Lumen integrate with other PyTorch libraries? For example, if a model didn't exist in Lumen, but did exist in another library, could you use that model inside of Lumen? Yes, to some extent. So, as I say, models in Lumen are expected to have a head, a body, and a tail. So, depending on what usage the model that you're working with has, that would then determine whether it should go in the head or the body. If you wanted to integrate it, then you would probably have to wrap it inside a Lumen head module, basically because there's a few arguments, attributes, methods that a module is expected to have. That would be fairly easy, I think. However, it's at the moment it's not trivial to do, but certainly it is doable. This package being used outside of CMS seems generic enough. Engaging with the community, yes. Say Lumen is designed primarily for high-energy physics. However, the actual first application that I used it for was in an industry setting where I was doing some predictive analytics work. So it's not strictly tied to high-energy physics. It's definitely not strictly tied to CMS. It's just that the package contains methods that are specifically useful for high-energy physics. So yeah, indeed, it can be used for anything. If you want to, it's not even tied to PyTorch, for instance. So in the CMS analysis I'm working on, we're saving the models, training the models in PyTorch, but then exporting them as a TensorFlow protocol buffer, and then using that in CMS software. So you can export in most formats that can be converted to from a PyTorch model. So there's an Onyx output in PyTorch that can be used to do that. This is now finished. So this just took over 3 minutes to train 3 models. We get a summary of the training here, the averages of the loss and the AMS. Now, it didn't actually return the trained models. Instead, it saved them. If we look in this results, it did get returned. We get the path to the model and the score to the model. Now, what we've done here is we've instantiated an ensemble of the models from the results. So it's picking up on this path. We can save that. We can apply it to our validation data. So here we're doing test time augmentation, all 8 possible combinations of the data of the events. That's just running over there. We can extract out a data frame from the fold yielder. So now we've got the targets, the weights of each event, and the predictions. We can plot those out. So just your binary classification shapes here. These are normalized by luminosity, We can also do just plot the density as well. And then the aim was to optimize the AMS. Now, what this method is doing is it's picking the best cut on the data such that you optimize the AMS. However, that's just based on a single data point, and it's not necessarily guaranteed to generalize. That cut isn't guaranteed to generalize to unseen data. So what I've actually found is it's best to compute the top 10% of cuts and then take the mean value. That slightly reduces the AMS, but it provides a more generalizing cut. And finally, we can apply this to our testing data. We're just computing the public AMS here, what we would see during the competition. Yes, that, yeah, 0.381. So that's near the top of the public leadership board. It's at the top of the public leadership board, near the top of the public, at the top of the private leaderboard. We can further improve the score if we were to train more models in the ensemble. Finally, just to show, we can interpret the model, compute the feature importance, for instance. So here we're running over all 10 folds of the data, computing the mean, computing the uncertainty, and then we're repeating that for each model in the ensemble. Finally, we can plot out the feature importance plus the uncertainties on them. We can see that it relies on a mixture of derived and primary input features. So I'll finish off answering the questions. Is the training testing data also? Yes, so if you grab the data from Kaggle, it's there's only labels for the training data. The testing data is included, but there's no labels for it. So if you want to get a prediction, then you actually have to submit your predictions to Kaggle. On the CERN Open data, you get the labeled test data. You have to be sure to split it out from private and public yourself, though, so you don't get double the luminosity. You showed data augmentation via rotation. Does Lumen provide a utility for the opposite approach of aligning all events in the same way? Yes. So this process proc events method, proc event method here. So there's fix phi, fix y, and fix z. These will, if you set them to true, it'll try and rotate all the events to have the same common alignment. And that's using reference vector 0 and reference vector 1. So it'll set all the events such that reference vector 0 is at phi equals 0. And it will be in the positive z direction. And then it will also then flip the events such that reference vector 1 has a positive y. So yeah, you can remove all symmetries from the data using that method. In this example, I found it's better to actually keep the symmetries and instead apply data augmentation. But obviously that takes a bit longer to train and to test. What are the zero matrix elements? Okay, yes, that's nothing to do with reweighting. It's to do with the fact that you can actually pre-process all your data into a matrix. So if you're working with image data, I put out a paper earlier this week in which we were working with a 3D grid of data. And in that case, we were already processing the data into a matrix format. And that's where this matrix elements comes into. So it's nothing to do with matrix elements in high-energy physics. It's matrix elements in the data. So yeah, it's not being covered here. If you look at the RNN, CNN, GNN example, then eventually we'll start using the matrix elements towards the end of that tutorial. So yeah, so I went a bit over time there.
That's all right. All right, we will take a 25-minute break now. And yeah, I don't know what that is in CERN time. And after the break, we'll be doing 2 talks on Julia. So very exciting. And yes, make a cup of coffee and see you soon.
Hi everyone. So we're back to the very last session of this week workshop. So it might be like a funny joke that we have a session on Julia specifically, but this actually came as a nice spontaneous discussion on the HEP Software Foundation forum. I think this is very welcome because if anything, it can only be positive first of all. So we're very happy that in fact we have 2 contributions on the experiences, and there's even a paper behind on some studies for Julia in high energy physics. And then to really close the workshop, we will have a short half an hour of more open discussions on top of the usual discussions you might have on the specifics of the presentations themselves, since this seems to be quite a hot topic at the moment. And then I'll have just a few handful of slides, a couple of pictures from registrations to close out the session. So for now, thank you very much, Jan, for jumping in and presenting on your studies on Julian high physics. So I think you can share, and please.
Okay, thank you very much for inviting me to give this. Oh, sorry, this is not good. 1 second. You would think that after a year of COVID, I have set up my Zoom, but I have a new setup, and I'm afraid I have to quit and come back in a second here.
Okay.
Apologies for this.
All right.
I'll be back in a minute.
These things happen live, but there's no problem. We can recover quickly, I'm sure. Right, Jan. So I see you back, and I made you co-host, so you should be able to share again. You are muted, but I have made you co-host. If you can hear me, you should unmute.
Very good. So
Okay.
Apologies for all of this technical nonsense here. I hope you can see the slides. So thank you very much to the organizers for inviting me to give this presentation. My name is Jan Strube, and I will tell you a little bit about how I have used Julia in high energy physics analysis. So we're gonna, PowerPoint, there we go. So the goal of this is not to tell you that Julia is the greatest thing that you've ever seen and you should just drop everything and move over. Rather, I want to show you that Julia is productive. I have solved a couple of problems in high energy physics using it. Of course, there's always more than one way to do it. And I want to demonstrate here that Julia is one way to do it, and it's a very productive way. There's a list of case studies at Julia Computing if you're interested in how other people are using it. So then you can find out more there. So I will not give a comprehensive overview of all the language features that you have. Rather, I'm going to tell you a little bit about a couple of use cases I've had and the features of the language that enabled me to be productive in these use cases. So I will specifically talk a little bit about the interactivity and ease of use. And then we've had a little student project where we implemented convex hull for a 3D shower shape in a calorimeter. And I'm going to say a little bit about that. Then I will have 1 or 2 slides on the interoperability with Python and C++. Obviously, that's important, specifically Python for this conference, but also C++. Obviously, there's a lot of useful C++ HEP code. And I'm going to show you how we interface with that. And then just an example for an algorithm that we implemented in pure Julia. And then I want to close out with wrapping all of these different pieces up and tying them in a multi-threaded processing application that I think just demonstrates the different workflows that we have in high energy physics. So I don't have a lot of specific code examples. I think the scope of this talk would just be too much for this talk. So there's links in the slide deck. If you click on the links, there's a GitHub repo that you can look at that has all the code examples that we used in our paper. The paper is linked here as well. So if you're interested, I invite you to click on this and follow along that way. Okay, so like I said, I'm not going to give a completely comprehensive overview. This is too much for this kind of talk, but I want to give you a specific example. So we had the following problem. I wanted to study ILC calorimeter clusters. They have thousands of hits. They have 3D shower shapes. So what if we treat them like a rigid body and improve our analysis of the particle ID in the calorimeter that way? I had a student with a strong background in computational methods and an interest in visualizations. And I had a lot of linear collider IO, LTIO format files. So I didn't want to convert everything first before the student could be productive. So I wanted to have something that would work with that format. And then I had a couple of issues I wanted to solve, algorithms that I wanted to implement, fractal dimensions, and a couple of other things. So it was important that the language that we choose just is easy, makes it easy to implement these algorithms. So I had the following options: C++. The student didn't know C++. I didn't really want to spend time teaching all of the concepts behind memory management and help debug segmentation faults. So we didn't do that. Java would have been fine. He had actually used Java in his class. But then I would have been left with a lot of Java code, and there's just a shrinking role for Java in HEP. Python would have been okay, I think. We could have done, implement the algorithm naively first, then improve the speed of the slow parts. But I thought I don't want to go through this. I want to skip this kind of speeding up step. I want to see if Julia can help tick all of those boxes. And I knew that it had been used for numerical algorithms. I knew there is good support for linear algebra. I had written the interface with the LTIO, so I wanted to see if this works for us. So then let's talk about the interactivity. The Ju in Jupyter is actually for Julia. So the interactivity has been there basically from the beginning of Jupyter. Julia was part of this ecosystem. I don't have to tell you that it's excellent for teaching. And I think especially for summer students, for students who implement new algorithms, who learn new concepts, this interactivity is really key. Julia works in these Jupyter Hub servers at DAISY or at CERN. As far as I know, without problem. I've been using it a lot at DAISY. Another thing that's useful and important for summer students, I think, is this excellent support for packages. There is very little need, or in my case, there was no need to compile anything. Everything could just be installed out of the box. There were no version incompatibilities. Everything just was there. And I think the reason for this partly was because Julia has this excellent support for packages baked in. You have a package mode in the command prompt in the REPL. There's a central registry where you, if you feel like your package is mature enough, you register it there, and then everybody can just add your package from that central repository. And an important feature is it has native support for tests. So that really encourages people to just include tests by default in their packages. And that has the advantage that a lot of these packages have tests. And if you want to know how to use the package, the tests are a good first step to see how these features are being used. Another thing that is very useful is the core language features, or many of the core language features are implemented in Julia. And that really reduces these conflicts that you have, for example, between NumPy, TensorFlow, PyTorch. They all have their own data representation, and you have to translate it. If you want to use the two of those packages in the same program, you have to translate between the data representation for each of those packages. And in Julia, All of this is done in Julia, so these packages are a lot more composable than in Python, because you don't have to go through a third party or third language implementation. So coming back to the analysis of these calorimeter clusters, as I mentioned, this project was exploratory, so I needed interactivity. I wanted good support for linear algebra. The summer student didn't have any prior knowledge of the ILT physics, and I wanted to spend most of my time teaching that rather than some details of programming. So it was a computer science student. They had taken a Java class, and I wanted algorithms to be straightforward to implement from A, that class, and B, a couple of papers that I had found. And then maturity, as I pointed out, I didn't want to debug installation issues, and I also didn't want to be the only point of contact. So I wanted to make sure that there is enough information online where the student can just figure these things out by themselves. So that again was why I thought Julia is a great choice for this project. So let me tell you a little bit about how successful this was. So here is what the project was about. You have these hit energies. You have a point cloud basically in 3D. Then you blur the density grid that you get from this point cloud. Then you generate the isosurface using marching cubes. And this marching cubes algorithm, actually, the student implemented by themselves from their class. They had done the 2D implementation in Java in their class, and he just did the 3D implementation generalizing to cubes by themselves using Julia. So this ticked the box of, is it easy to implement an algorithm? So then when you put this together, you see these shapes, and the visualizations here are done in Blender. But the data obviously is generated in Julia. And you see these different shower shapes. So pions look by eye very different from electrons, which look, again, very different from muons. So can we utilize that information? We generated these convex hulls around the shower shapes, and then we used a couple of volume ratios, for example, and on the next slide, I'll show you another item to separate these shower shapes and to do particle ID in the calorimeter that way. And there's a link here on where this code is published. So this is the result of this little project. I don't want to go into too much detail here. The fractal dimensions were implemented from a paper that was published at the time of my study that somebody else had done, and we just took this code and or took the paper, the definition of the algorithm in the paper, and implemented that in code. And then our work was captured in this moment of inertia. So this gives you a different dimension, a different angle to look at these particle IDs in the shower. So I think this was a very successful project there for just one summer. Okay, so then let's go to other features that are useful in high energy physics. As I mentioned, language interoperability is important. I don't want to rewrite everything from scratch. We had examples where we implemented, HEP analyses in other languages, and that really forced us to write everything in that language, and just I think that didn't work very well. So there is a lot of C++ code. In Julia, there is support for wrapping libraries in something that looks like boost.python. So if you've written code like this, then this way to wrap C++ code for Julia should be very familiar. It requires a bit of boilerplate code, but that also has the advantage that it gives you fine-grained control over what this binding, what the C++ library should look like on the Julia side. So for example, a lot of times you have these casts in C++. By combining the dynamic features of Julia and the fact that you have to write a little bit of C++ code, I was able to just avoid these casts altogether. The track in Julia always has the right type because Julia is strongly typed. But the code, the casting code, is now baked into the binding itself. So this could actually be pushed upstream into LCIO proper, but this lets you give this gives you some fine-grained control over what you can do and how you want to expose the API on the Julia side. So there's a couple of libraries that wrap C++ libraries, LCIO, FastJet, and there's a bunch of additional ones, and I invite you to go to JuliaHEP on GitHub to find out more packages that wrap C++ libraries useful for HEP. Julia integrates well with Python as well. It starts being used actually as the backend for Python packages. So there's, of course, a lot of C++ based Python packages, but we also have Julia based Python packages right now. So there's diff eqpy, and this brings the whole differential equation solver ecosystem from Julia into Python. There is a package for symbolic regression that is fairly new that uses Julia on the back end. And so these packages are pip installable. You can just get them and they run Julia behind the scenes. You will never know that this actually runs Julia. The interaction also works in the other direction. Julia can use existing Python packages. So for example, there's a very nice plotting ecosystem in matplotlib that's all exposed via pyplot.jl. There is uproot is wrapped for Julia, and now there's also the beginnings of a pure Julia implementation of uproot. I just wanted to mention this here for completeness, but the interaction really works in both directions, and it's pretty transparent. Okay, so then we have ways to interface with existing code, but of course we also want to write new code in Julia. So here is an example of implementing the Fox-Wolfram moments. Again, I thought this was a use case in HEP. I just wanted to see how easy it is to implement this. There is, of course, the implementation in Pythia in Fortran 77. So I just wanted to see how easy is it to implement that to Julia, Python, and C++. There's a paper that claims reproducibility and implementing this quickly from a paper is a strong requirement for reproducible research. So I didn't spend a lot of time optimizing the code for the respective language. I basically took the Fortran 77 implementation and just copied and pasted it, fixed the bugs, and that's it. So with that, at that level of work, Julia was the fastest choice. There's no doubt that I could improve each of these performances here, but just from this level, Julia was the fastest. And of course, Python was terrible. No question. There's a nested for loop here. However, it was very easy to speed up the Python implementation using Numba, and that even got me faster than C++. So that, however, comes with all the pros and cons of mixing two languages. So it was, in this case, it worked well. I don't know how much time it would have been to debug it had it broken, because I don't know anything about Numba. But if it works, it's great. Okay, so then if we talk about speed, let's talk about parallelism for a second. There's very good support for parallel and concurrent programs in Julia. We have green threads, which is the Go-like concurrency model. In Julia, these are called tasks. So you can just schedule, you break your program up into thousands of pieces, and they will be scheduled onto the available hardware threads. You can specifically talk to these threads and schedule these pieces yourself. If you want to have more coarser grained control and really know which piece of your code runs on which thread, that's possible. A fast way to split this up by threads is to just put this threads macro in front of your for loop, and then this for loop will run in parallel on the available hardware threads. So in this case, if the array A had at least 100 elements, then after this loop, each of them would contain which available hardware thread this piece ran on. There's multiprocessing, and that's a little bit like the Python processing module, multiprocessing module. And this gives you same node and multiple node processing, so you can also talk to different nodes that are connected via SSH or MPI. And there's good support for GPU programming. I don't have an example of this, but there's the Julia GPU organization that has more information here. Okay, so then let's talk about a use case for processing these LCAO files in parallel. In this case, it was an example for me of a library that is not thread safe. And I think we have a couple of examples like that in HEP. So what we did was we wrapped each instance in a separate process, and then we communicate via these channels. So each file, it lives in its own process context, and each LCAO process has its own memory space. So there's no problem that these libraries are not thread safe. They don't talk to each other. So what we do is we read multiple files at the same time, not use multiple processes to read the same file. And then we have an implementation of the event processing where we process the events in parallel. So the events then are pulled from this queue and processed. We have Fox Wolfram in this processor. We have Thrust, and we use FastJet, just using the C++ bindings. So we combine a Julia processor with a C++ based processor in the same function, and we schedule this in parallel. So here is a little schematic of what this looks like. One hard drive, we have a number of LCAO readers. Each of them runs in their own process. Each of them reads a different file. So in this case, of course, a lot of times you have multiple files in HEP. So in this case, it was easy to parallelize it that way. They all write to the same queue. And then there are these multiple processors. Each of them runs Fox Wolfram, Thrust, and JetFinder, pulls one event from the queue, writes it to the next queue, and we run multiple in parallel. And then in the end, we just aggregate the results to force this to until the last one is finished. So here's a quick result of this speedup test. Again, this is not the fastest way to do this. This is just a use case where it's simple to put these different pieces together. It's simple to just change the number of processes that you schedule. We had, in this case, I think 20 threads. So I didn't oversubscribe the CPU here. We could have easily done this, but then, of course, I would expect the performance to drop if you oversubscribe, because then there is contention. So I wasn't really interested in all the details of this CPU. I just wanted to see how easy is it to schedule different processors, and do we really see at least a reasonable speed up. So what you see on the x-axis is how many files are being read in parallel. And you can see basically even with one processor, so one function that does the event shapes and the jet finding, if you have 4 readers that feed that queue for just one processor, you basically get linear speed up. So this really shows you how I/O limited this application is in this case. And then as you schedule more processors, you get speed up. So scheduling 19 processors, where I said we have 20 hardware threads. The 20th then runs the main thread, so I didn't oversubscribe that one. So at 19 processors, you get a little bit of slowdown. Again, I didn't go into details of why this is. I assume there's contention at some level. The details depend on your own use case and on your workload. So just debugging this and speeding this up for this very simple toy model, I think was overkill. So you get quite a bit of speed up over the single threaded application, and comparing the wall time change. This is just a different way to look at the same information. So you have a very easy way to speed up your application in this way. Okay, so summary. I felt that the support for interactive programming, the package manager, the integrated test suite really helped getting newcomers up to speed quickly. They have confidence in the packages that they use. There are tests, and if they don't know how to use a specific package, they can just look at the tests for examples. The support for distributed computing and multi-threading paradigms really enable the efficient use of modern computing architectures. And in this paper and in the code examples, I've shown you how to wrap this into these processors in the distributed paradigm with its own context for each process, or the threading model if you have thread safe libraries. And so you can mix and match those two paradigms. You can mix and match C++ and Julia libraries in this way. And then the interoperability, of course, with C++ and Python is key in high energy physics. So in summary, I think Julia is a very good option for productive high energy physics analysis work. Thank you very much. I'm open for questions.
Thank you, Jan. Thank you very much for sharing your thoughts and studies. I think we still have a few minutes. So if you have the web page on Slido, is that easy for you?
Oh, I do not have it. Sorry. Maybe it's easier if somebody shares that screen. Apologies.
I can share that. So I can do that. You should be able to see that now.
Yes.
So we can probably go through a few questions. I should remind everybody, by the way, that more even philosophical questions, we can still have it during the last open session. So maybe something specific you can pick up from here. Okay, so maybe let's start with the per project environment, like virtual amps and Python, that there's support for that. So you can have a project. It's called a project directory. So each project directory has its own set of packages and version numbers, and they're all independent. There's a central part where these packages get downloaded, but each project just loads the versions that you want for that project. Okay, should I keep doing my stuff in Python and Julia? I think it's productive to use Julia. As I've pointed out, there are packages that interface. So there are packages that do the heavy numeric tasks in Julia and just expose whatever they need to Python. I think it's a good use case, but this depends on the individual, I guess. Virtual env conda is not present in Julia, so we've had this, right? Binary depends are managed by the same package system. Okay, we have this. There's a Julia con talk where you can look for more information. Thank you for the comment there. Okay, so let's do, how difficult was it to write the wrapper for FastJet? The easy answer is look at the code. It is not terrible. I had experience with LTIO before, so I knew what I was doing. But this is, there's a cookie cutter part to it, where you have this boilerplate code that you always need, and then you expose only the API, the part of the API that you need. It took me maybe a day
What is thread safe? Well, okay, this is kind of an obvious question. It means that you can use that application from multiple threads. So if there's a global variable in your application, that is a good sign that your application is not thread safe. If different threads, you know, modify the same piece of the memory at different times, then you don't know which one was first, and so that is not thread safe. Environments method version. I would encourage people on the environment. I would encourage people to use their own project directories. I think that's just useful. At the moment, it's maybe rare because there's still, well, I would encourage people to use different environments. That's just it. Okay, FastJet. I think we got through all of them.
I think we've been through everything. I'm sure we will probably come to some the first questions where you would probably have more discussion, but that I think we have time to. So we have precisely on time. Thank you again very much, and
thank you.
Forward to more discussion in half an hour or so. So now it's up to Philip. I see you here, and you should also be able to share.
Hello, can you hear me?
Yeah, it's all fine.
Oh, perfect. So are you sharing this? No, I should share.
You should share, it's easier.
Yeah. So I didn't put the Blinder link on the GitHub, but anyway, it's more like a presentation. So I think anyway, it's better just to follow the presentation than trying to run the code. So let me. So I first like to thank the organizer to have included this Julia session in this PyHEP 2021 editions, and to have give me the opportunity to give one of these to talk of this sessions. So first, introductions that have Jan showed experience. Julia is a new programming language, and actually is even new, quite new for me, because I discovered it while I was making a survey for programming language for the QP experiment, so notwinless double-bit experiments. So this was just in this started in last April. So the idea was to know which language we should use for this coming experiment. And so it's new for me, so I'm not biased by use of the language, and I've also actually learned it by preparing this talk. And this was as fast as learning Python, and maybe even faster because there was a lot of similarities. So I will present Julia to you in the perspective of using it for HEP application, and more particularly for LHC. So, sorry, yes. I try to avoid the scrolling, but okay. So first, the context. In HEP, and especially for LHC, high performance computing is central. So here you have the needs for CML, and similar for the other experiment of LHC, the current need and the projection for HLHC. So on the left is the CPU, on the right is the data storage. So it gives also an idea of the size of data that we are processing. On the left, the unit is a tera CPU times seconds. And you see that in 2027, we reach 1,600 tera CPU seconds. And this corresponds to nowadays CPU with 10 cores. So computing plays a role in the theoretic prediction, so the simulation of the proton-proton collisions, in the simulation of the detector response. So this two appears as the MC on the left plot, in the reconstruction of the physics events that appear in the prompt data and non-prompt data, and the most of the data that are on the right, everything except the user. And the analysis, and then the final step is the analysis of the reconstructed events, so that we call physics analysis. And what we should notice here, and what is very important, is that this analysis part is a substantial part of the CPU that we are using. So the analysis of events, of physics analysis, behind each result publication, each publication of the experiments, of LHC experiments, we have tens of thousands of computing jobs that have been run on the worldwide computing grids. And we are publishing thousands of papers. Last summer, both ATAS and CMS celebrate their respective anniversary of their respective 1000th paper. So C++ is widely used, and its performance that just far is essential. The research, the code that we are writing here is a research code. So this is developed by the main authors of the prepared publication. This is a physicist. And so Python is attractive actually because it is fast writing of code and fast writing of code, and it's especially important for code that is just done for publications. And also for the library ecosystem that goes with it, and especially for machine learning. But it does not meet the performance that is provided by C++. So how we deal with it, that we actually used in conjunction C++, and there was a huge development that's underway, and this is thanks to many people from HSF, on to leverage the performance of Python, and always the principle actually is to move the critical part in the compiled part. So, but the more attractive things will be to have a programming language, is what I thought before learning Julia, that offer both pros of C++ and the pros of Python. So high performance code and fast writing code. So this, as you will learn before in the previous talk, this is already on the market. This is Julia. So Julia is solving this two language problem. So this is actually not specific to HEP. I think is in the many research domain, and this is people from the statistics domain that solve it. So in 2009, they had a quite ambitious idea of developing a language that would do both fast and easy coding and fast running. And in 2013, comes out Julia. So the birth of Julia was the 0.1. So this is really a breakthrough, and it's really recognized by different awards. I put it here. So since these conceptualizations, there was 12 years that passed, and a lot of development that have been done. And since these 12 years, and also 5 years, in 2016, I think HF had considered Julia. So since these last 5 years, there was a lot of things that have been done, and Julia has improved a lot, and from release to release. And they also aggregated many package developers, and we'll see that in the next. So for Julia, so you see, it can be used for HEP, and Jan has published a paper recently with Marcel Salinsky on the performance of Julia for HEP. So actually nowadays, Julia is a mature language with a wide ecosystem, and what I will show today. So I want to make some parentheses on loops. So you will, I think you will know why we come to with looking at these pictures. So HEP, a data analysis, is a looping game. What we do, I mean, we are looping on billions of LHC events, and for each event, we are looping on tens of hundreds of objects, which are particles or particle candidates. And in the events, what we do often, we do matching and particle matching, clustering, jet clustering that Jan discussed, combinations, which means that for each object, we again do loops on the order of 10 of hundreds of objects. Actually, these outer loops hide several loops because there are so many events that are spread in several files, and we have different data sets. So they correspond to simulation data with different trigger streams and different physics events. And this loop of loops is actually repeated several times for each analysis, because the process that you do the analysis, you look at the results, then you improve the analysis, you look at the results again and again until the publications, and this process can take several years. So actually a line of code is executed billions of times, even for cleanest code that was just developed for publications. So why I'm discussing about loops? is because Python dislikes loops, contrary to the snakes that we have seen on the picture. So a master rule for high performance computing in Python is to avoid writing loop. So how we do this is that actually we push the loop down to underlying compiled libraries. This is the approach of the NumPy vectorization. So in such way that the loop is done in compiled code and high performance codes. But the code that we have to run here for the analysis is a code that we develop for the searchers. It's not a common code that we can use from a library which has already done. So let's make a small test for a loop. So let's loop in Python. So here I define a simple function. So I just want to compute the sum of the 1/n series. So I define the functions, then time it, and it takes 120 milliseconds. So it took that 19 milliseconds yesterday. Okay. So is it fast? Is it slow? We have to compare with C++. So let's we just remain at Python is order of 100 milliseconds. So here's I implemented in C++. Sorry, I should not spoil too much. So here's the code is similar. So you have a get time of day is just to time the code, and here you have the loop that you see here. I don't know if do you see my pointer?
Yeah.
Okay, right. So since it's compiled, you need to compile it. I compile it with two options, with default option of GCC and with the maximum optimization, which is -03, which makes sometimes more difficult to debug when you run the debugger. And what do we get? Is it runs 5 milliseconds. So I probably zoom that is slowing down my computer. So for 5 milliseconds for without optimizations and 2 milliseconds with optimizations. So we keep what we remind for here, the output of this is that it takes 60 times faster with C++. So now how is it going with Julia? So here's the Julia code. So it's now you see how Julia code looks like. So you can see is similar to Python. So you have different functions. So is the accumulator. So a few difference. You don't need the colon at the end of the for loop or if loop. You don't implement indentation. So no more bugs because you deleted an ident or you added one. But it's still, I mean, it's still as compact as a Python because anyways, the line with the ands you need in the Python. I mean, you will put in anti-line in Python if you format properly your code. And also there is like in Python, you have many sugar. Is it how you say sugary or sweets in the language? And you see that here we have the underscore that makes it easier to read the large numbers. So let's just run it and time it. And here it took 1.7 milliseconds. So I know this by chance is even faster than C++, but when I did the test, it was similar. So actually, sorry for the small fonts. So it took 90 milliseconds for Python and 60 times less for Julia, and this Julia is the same performance C++. So now, performance is not the only thing because we want also to have is programming. So what you have seen before, we already seen that the syntax is similar to Python, and so we don't have any more std map, std vector, and you don't have the compiling step either. So another thing which is important is programming nowadays is a community. So it's easier to program in a language where you have a large community that is using it. Why? Because what we are doing nowadays, what I'm calling Google programming. So it's when you don't know how to do something, you just go in your preferred search engine, mine is the Go, and you type something, you type what you want, and you will go you will find how to do it in Stack Overflow. So this we can try it. Maybe, yeah. So I don't know what I want to do. If Julia, if I want to search a string, search in a string. And you see, you have many things. Strings in Julia. Okay, I want this. It's consonants. And this, when I learned the Julia for this talk, anything I was looking for, I found it on the internet. So let's come back to the talk. Sorry. So yes, it's open is the same. Okay, sorry. I use Surf to have a full screen, but I don't know how to go back. Back is control. Control H. Okay, I did the H and Control H. Was supposed to open in a new. Okay, fine. So now another. See, I lose time. So another important reason of success of Python is the ecosystem. So I knew before this workshop that there was a large set of library and an active development for that set of library for Julia, and this is growing. And in addition, Julia is firstly used by scientific community, so the libraries are oriented to our needs. But during this workshop, I did the following games that anytime someone mentioned a package was using in Python, I type in the DodaGo the name of the package and Julia. And I was amazed by the results of this game. So this is here. So this is all the package that was mentioned. And the check mark means that there is a package in Julia, and of course there is no package. So there's only two. There is a FreeCAD, which has no binding for Julia. And actually, there is an active discussion among the FreeCAD developers about Julia, and FreeCAD is actually suffering. The developers are suffering of a double language problem, and moving to Julia would actually be a benefit for them. And there is a hypothesis, which is used for testing code, which is not in Julia. There was one, but is no more maintained. But there was tools to test, as Jan mentioned. So now another important thing that we have analysis the data, so the data format, the support for data format. So for non-HEP, you have many things. For HDF5, for packet, for root, as Jan mentioned, there is the uproot and the unroot. So I think we are missing a solid and performance library, and this, if we want to move to Julia, it's probably the first things to address. We have to build the package, we consolidate unroots. So this package was developed by a physicist that wanted to use Julia to do the analysis and needed to read the data from the experiments. So when you develop, there are also needs of advanced tools. So maybe I will skip this because I'm running out of time. So, but I know because this is important actually. So there is IDE. So if you have support for Emacs and Vim, and people that are used to more advanced integrated development environments, there is a very nice plugin for Atom and also for VS Code. And actually, it transforms this IDE as a framework to do analysis, because you have the plot, you can run the code there, and you have also a nice debugger. And you have notebooks, or you have a Jupyter. Jan mentioned Ju is for Julia, and you have also a notebook which is called Pluto, which is specific to Julia. It's a new generation notebook where the cells are automatically updated. So in Jupyter, when you modify a cell, if you have to run again manually the cells that depends for which result depend on it. Pluto resolve itself track the dependency, and we just update the cells that depend on the cell that you updated. So there is all the developer tools that needs. As Jan mentioned, there is a good support for package installation. Actually, Python made it easy with Kunda and PyHEP, and it's even easier with Julia because you have is part of the language of the library, the main library. And so everyone is using the same. And in addition, if the user is including a package is missing, it will just give the instruction how to install it. So we can try. If I do import link, I get this message. Just run import package. I copy this code and we will install the missing package. Okay, so Julia has also a rep command, so like IPythons, and here's a special mode for the package. So I want to come to another topics with the interoperability that make the. So I will skip this because Jan addressed it. So even better than you must more than me. Actually, I already planned. So I put for reference the way how to call different language from Julia. And now I will go to HEP, to an example of that. So let's use now HEP for on the Julia on the HEP examples. So I used the CMS Damion spectrum analysis on the park data, which has actually used as a sample for many by many of us. So one caveat is you have to keep an extremely simple analysis, and it's way far from a usual LHC analysis. So let's just start and try this. Okay, so this analysis is consistent measuring the Damion spectrum, the Damion mass spectrum, and let's use the data special data that were stored, that we call park data, we stored a reduced, which just stores those objects that we needed to do the analysis. So when we took the data, so the Muon was reconstructed online, and this allowed to register more data, and allow us to reach a very low mass in the spectrums. So this is this also. The consequence is also that the data set is quite simple. So you just have the muons. So here you have the information on the spectrum. So on the analysis, sorry, you have the spectrum. Here you see the Zig peak, JEPSI, and you have the reference to the paper. So now let's do it on Julia. So this is what you have in the data set. So to do the analysis, we need some tools. So you need to do histogramming. So histogramming in is a bit different than how it is done in other fields. So I mean, it's very simple to do a histogramming package. That's probably why we have so many in Python. And we also need to store for momentum. So this is what I have in another notebook. So we don't need to do the detail of this. So we need the data file. So this is already downloaded, and then we need to read the data. So this is the function to read the data. So I don't know if I come in detail on this. Probably it's not so. Yes, no. So interesting. I would just go to the analysis. So now let's come to the analysis. So just to say what this function do is that we just read the file fname that we provide. They read it and provide the events that is read, which is actually just muons here, to a function that we pass to it, and we can limit the number of events process. So here is the analysis, the code. So you see, code is very similar to things as the Pythons. You don't need to mention the type. Also, we often mention it when we define the structure, so the classes. And even if you don't mention it, specify the type, the compiler find it and make efficient code. So we define the histograms, and we fill the histograms with the diamond mass that we compute. So we read the event. So here's a special construct which is very nice in Julia. So this do, which some actually do something which is used in place of the with construct of Python, but is more powerful. So what it does is actually define anonymous functions or lambda functions, which is what is after the do here, and it just passes functions to the previous call, so this read. So if you remember the read that I showed before function, take a first argument that is the functions. So what will we pass? So this we don't write it here, and actually the compiler will pass the functions, the lambda functions, which is implemented in this do block. It passes functions, and then it executes this block. So the read will execute this block, and the muons here, we see muons is a parameter of the functions that is passed when the read function is call it. So this is very powerful. So this, and I mean, this allows to make a neat code, because you don't have, if you would do that with a lambda function in C++ or in Python, this code will go inside the parentheses of the read, which make quite a clutter code. So the analysis sample we request exactly 2 muons. So this is the length of pure muons. The 0 axis to be 2, so it will be muons.size in Python. And we ask to have the muons to have opposite charge. And so is there
Philip, you've got 3 minutes left.
Sorry, yes.
Yeah.
And then we just plot we compute the mass, and we do the plots. So now, okay, this is what I explained. So now we can run the code, and let's see. I'm just surprised by the. Okay, so it takes 30 seconds. Maybe I should not run it. Okay, so it takes 30 seconds. You can believe me, trust me. So now let's. Oh yeah, but I will need it to make the plot. So maybe I will go to the questions, because I have just 4 minutes left. So just to say that we have also, okay, it's done. So we have also many language, but in addition, what is something nice that we have we have language that provide a common front end for the different language package. So give you an interface, a common interface. So here is the code to make the plots, and you have a nice plot, which is here the diamond spectrum, like we've seen the one from the paper. So that's things that. If you prefer data frame, we could also do the analysis with data frames, because Julia is also supporting data frame. And these are also the equivalent of Dask, so you can do parallel computing. Okay, so we just go back to the so so anyway, yes, okay. So this was my end of my presentation. So Julia offers the, what is this? Oh, I have someone writing. I see something. I don't have anything else. Okay. Can you hear me?
Yeah, yeah, we hear you.
Okay, so I don't know. I have now black screen.
Slides are gone. Yeah, it's a
okay. Anyway, so you have seen the conclusions. So now, I mean, we can go to the questions, then go to the discussions.
Okay.
But can you tell me the questions, because I don't know why I have a black screen. So I I mean,
Okay.
yes, it's back. It's back.
It's back?
Yes. Okay.
Otherwise, I can just share it for you. You see that now?
Yes, I see only two.
Yep. I
Okay.
suspect people are waiting for the discussion.
Yes.
So, all right. Okay, please go ahead.
So the first question is what is the underlying difference between Python and Julia? So in terms of usage, Python is much faster, as I show, and in the implementation is that Julia is doing just-in-time compilations, and by natively. It's not so it's a bit similar to the Numba, but it does with everything. And okay, and there is also a nice feature, but okay, of a multi. Okay, but yeah, I mean, there's also the nice feature which is called the multi-dispatching. So it's something that extends the object-oriented programations, and that actually allows to reuse much more to reuse code of others. And I mean, actually, the developer of the program of this language were surprised by how much is improved the reusing of code, and it's very easy to improve code to reuse code of others. Actually, so in object-oriented in C++, if you want to extend the library, what you usually need is to ask the authors to change the class, because you need to add the function to the class. So in Julia, you don't need. You can just extend the class from and add the functionalities. And this makes it code much user. So actually, it brings together the templates, the generic programming, a template, with the object programming. And the also next question was how many? Oh, for the how many events? I don't remember. This is I don't remember the number, but it's a full data set. It's a full data set, so it's this was on the Run One Park data set. So to give an idea, so doing it on Python with using a T3 takes 4 hours, 4 hours and 50 minutes. And I think with add data frame and Sklink, it takes something like 20 minutes, I think so.
I see a couple of questions more, but actually, I think this is pretty much already part of the discussion. So
yes, let's go to the discussion. Yes.
Yeah. So let me stop sharing. And so now, so yeah, for the next 20-25 minutes, we would like to make it easy for everybody. We should go through those questions, but let's allow you to. Oh, there's an echo.
So maybe I have to mute.
Yeah, just so yeah. So we're gonna try and make it live. So actually, the people who posted there, if they can, they will ask the question live. For certainly some of the questions I saw there can be asked. So I'm going to allow people to unmute themselves, but please do respect that everybody's turn in making questions. So if you want to ask a question or have some opinion to bring up on the table, just raise your hand as Ben is doing right now, and we can take it from there. So let me first of all allow that anybody can unmute. So I think Ben is actually going to start then. Please, Ben.
Yeah, thanks. I mean, firstly, thanks for both the great talks, right? But my general question, and I'd be really interested to hear what you think, but also what everyone else thinks, is it sounds so good. It sounds like a very interesting language, but what will be the barriers that you see at this point for people to move over? What's going to stop people moving to Julia, in your opinion?
So if I can speak from my own experience, for me, the biggest thing was initially not being able to read my data. And that was a bit of threshold to implement the reader for that file format. But that was the biggest hurdle for me. I think the other thing is ecosystem. You can't have people in collaborations try out 20 different languages, right? The collaboration falls apart. So you know, at the moment, the collaborations are using two languages, C++ and Python. At some point, this is going to have a limit. If the collaboration decides as a collaboration to adopt Python, I think that would be useful. But if you start writing Julia code and then you move on and nobody can maintain it, that's not useful. So I think that is in these large high energy physics collaborations, I think that I see the biggest obstacle to adoption.
Yeah, I think if I can sort of reply, like, I think that's been one of the things we felt within PyHEP. It was interesting. I think we've played a good role of helping build and bring people together within high energy physics to you know, improve Python support. And I think something like you're saying, I think you'll increase the support, or increase the accessibility to it a lot if you can really make sure that the community is working together on it.
Now, having said that, I mean, the syntax between Python and Julia is a lot closer than some of these other languages. We've had examples with, you know, people trying Java before, and they're really, the interoperability was bad, and the only reasonable way to get this working is everybody would have had to implement everything in Java, and it's just that's just a non-starter. So yeah, I think that would be the obstacle. I think I think it would be a good choice. It's probably not too much overhead to add this, but the collaborations need to decide for themselves how much additional maintenance burden they want to impose.
Yeah, allow me to build my position. Just to make a comment, Edith, I think you mentioned the support of languages. It is for sure true that within the LHC experiments, which are big experiments, C++ and Python are fully supported, in the sense that probably it's the case that everybody except maybe LS are configuring their applications throughout the chain in Python. So that's really built into it, and I see there will be a large moment. That will be quite tricky to change that right now, because we're going to start run 3 and there are many other priorities, as everybody mentions. Now, where I see Julia could come into play would be naturally from the analysis side. So from the end of the chain, so to speak, which is exactly what happened to Python. So that I find interesting, especially for some of us who are old enough that I remember the move from Fortran to C++, because I did all my PhD in Fortran. Yeah, I think we will have a shift at some point. There will be a cultural change, and there will be some first explorers as yourselves in Julia. This is already happening, and probably, as I think Ben was mentioning in some chat yesterday, that the switch, if that's going to happen at some point, and there wouldn't, I also see problems with that change, by the way, but that will probably happen quicker than it happened in the past, because we have learned a lot, especially from looking a little bit outside ourselves. We were not looking into the data science world. I always tell people that don't forget there's about 50 million data scientists in the world, and many of them are using Python. That's why the system is what it is, right? And this is a big TGV, or a big plane, if you want. So, but I'm completely convinced, although I'm super enthusiastic about Python, that there is an interest in Julia. So I'll be very interested to hear what others think in those respects, having in mind all these constraints. So Philippe, you have a quick, please go ahead.
Yeah, I want to add this up. So I agree with you that first thing that can be done is for the analysis, and for this we need to provide tools, and first things to be able to read the root files in an efficient way, and maybe plus you also to have a binding to root, because then you have all the tools that you need. I mean, what happens for Pythons? But it's too late for LHC, but it's maybe the right time for HLHC. And if we start using for the analysis, and probably in the future for HLHC, then it will be used for reconstruction code.
And there are many other experiments. If you a few colorful plots from the participants, you will see that we're talking about 50 experiments that at some point connected or registered to PyHEP, for example. So it's not just LHC. Of course, it's a big 10,000 people, roughly speaking, a bit over that. But there's many other collaborations where the threshold is probably much lower. Ben, you want to take over from that?
Yeah, I'm conscious that it's so far just the four of us discussing. It'd be nice. I want to give others a chance as well, but I wanted to add another point, which is one of the things that's interesting with Julia is that whereas Python is the transition from C++ to Python is maybe easier to write or nicer to work with. It's easier to teach and so on. But I think historically, at least, was slower than C++. And so what you actually see now is still a lot of our Python libraries actually under the hood use C++. What would be interesting is if Julia is actually going to give us the opposite, because actually it's if it can be as quick as C++, you could have packages that are actually written in Julia, but then still get used from Python frameworks. So the transition to Julia could actually look very different to what the transition away from C++ to Python looked like. It may actually come in that sort of it could at least come in that way. And that was it. I'll take my hand down.
Well, Gordon is next. Maybe that's a follow-up. Please, Gordon.
Yeah. So one of the, I think it was, there was this workshop in Amsterdam, and I can't remember. It was an analysis ecosystem workshop. I can't remember the exact year. I want to say it was 2019. Maybe it was 2018.
No, 16.
Oh, 16. Okay. All right. So yes, a little while ago. But one of the things that came out of that was in discussing the Python ecosystem was how crucial it was to build these things we called back then bridges and tunnels. And this is sort of you already referred to it as one of the, Jan, as one of the things that you were having some trepidation about with Julia.
No, you muted yourself, Gordon. You muted. The sound is gone.
My back now.
Yeah.
Yeah. Sorry about that. My battery died, and I was ignoring the out of battery warnings to my detriment there. But anyway, these bridges and tunnels is a specific target for development. So, for example, uproot and awkward in the Python ecosystem, you might be able to classify under these. And these are enablers. And the idea is not that you start building up the whole HEP ecosystem in Python, but rather you provide the bridge between the current ecosystem and the Julia ecosystem, for example. And I think in Python, that's been quite successful. And there's certainly some features in Julia which I think are superior to Python, and specifically the just-in-time compilation. So I'm very eager to see this move forward. And with the approach of taking advantage of the Julia ecosystem and building bridges or tunnels to the current HEP ecosystem, be it the Python or the C++ or direct root loading, I think could be quite powerful.
Yeah, I agree with that. And so that's why I started with the file format. Once you have once you can read your files, then you're at least somewhat decoupled from all of this other stuff, and you can start playing around. And that's why I started with this LCIO binding first. And so just on that interoperability again, so there are these ways to do the boost Python bindings. There's also a very interesting discussion going on right now about, so there is a compiler called cxx.jl that is kind of falling behind a little bit the Julia development. So this was a very easy way to directly call into C++ libraries. So Philip has shown you a way to call into C libraries, but there, of course, all the symbols are easy to understand. And with C++, you always have the problem with the name mangling, and you need different ways to call into these C++ libraries. And so there's a very interesting discussion going on right now about using CPPYY to interface C++ and Julia directly, so that you maybe can try things out without having to write this boilerplate code for the wrappers.
I think that's an interesting point indeed. Yeah, I see Thomas is there, and maybe you have some complementary points of view, also from coming from a completely non-LHC experiment. So that very welcome that you're joining. Hi.
Thank you, Eduardo. Yes, I just wanted to first second Jan's and others' comments about once you can read your files, once you have this I/O problem solved for a specific language, then I think you have basically all the stuff you need to do your analysis. But I think for myself, what I have experienced with Julia, so okay, I'm a bit biased. I started using Julia when it was version 0.3 or so, 5-6 years ago. I don't remember. So I played a lot with it, but I'm also an experienced Python developer, and I maintain a lot of packages for low-level and also high-level analysis for our experiment, KM3net. And the things which I was constantly fighting over the years was always maintaining these packages which are combined with Python and different technologies to make them fast. So we went through many transitions of making this thing fast. So things actually are libraries. We always suffered from this issue. I think this is at least what I have heard. It's always present in many different experiments where you have these one part of the scientists who are the older parts, or to say it like this, we are used to work with for example, Root, the C++ frameworks, Fortran, and don't want to learn anything new. And this other part, the newcomers who are willing to learn new things, who use Python, etc., etc. So we always try to keep up with this Python thing and implement it, and have used many things to accelerate stuff from Number and then all the other stuff you can think about, PyPy, etc. And the main point what I want to say is that maintaining all this glue code over the years was a horrible experience for me, because of course the more things you have as a dependency in your library, the more ecosystems you also have to maintain, and things are changing. That's inevitable. So if you're using something now, next year it will change, and no matter what you do, things will move on. And if you have to maintain different languages and different package systems which are work together, then this will cost a lot of things. So actually we have spent a lot of time in rewriting things because someone used IronPython, or someone used some Cython or C-compiled stuff using some bridges and software which is not maintained anymore. And this is where I think Julia is really nice, because stuff which I wrote back then, even if because Julia has evolved from version 0.3 to 1.61 now, many things from 5 years ago still work, because not much has been changed there. So it's just one ecosystem, and the algorithms and the high level part are written in the same language. So yeah, but that's just my 2 cents which I wanted to tell you. Thanks.
Thanks. Before I pass it on to Wim, profiting from that you're here, and you are from KM3net, so a small experiment compared to the big LHC mammoths. But so how do people say, knowing also that you have been developing packages in Python and Julia, how is well, if there's an uptake of Julia compared to Python in KM3net, or maybe some other experiments you are aware of? How are things in there?
Okay, so I had some crackings in the audio, but I think you asked how Julia is used in KM3net, or how is this perceived?
Yeah, exactly. What's the uptake? Because KM3net is a smaller experiment than this big experiment, so the threshold is probably lower as well. It's easier to change things and try different stuff. So yes, it would be interesting to know how that works for you.
Yeah, so we are in an early phase of the experiment, to be honest, which means that you can play a lot more around. And luckily, I have many nice colleagues and professors who are very open to try out new things. And Julia is starting to pick up, but to be honest, I feel like where Python was like 6 or 7 years ago in our experiment. So it was just by a small group of people. They see that this is something which is worthy to try out or to build upon, but it's not really picking up much attraction. So we have a small framework where we can read most of our data. I use it. I built the whole monitoring system upon it. So I use Python and Julia for the monitoring system, which I built several years ago, and still maintaining it. There is reconstruction algorithms written in Julia, and also some other libraries like neutrino oscillation packages, etc. But it's only a small part. So this is something which still needs to shift. This, I think, it only picks up when more people are joining this train. But to me, it feels like Python is this big, heavy train which is just going, and people kind of ignore the stuff that we are using the wrong language, in my opinion, for the purpose. For me, sorry to divert just a few seconds. To me, it was like I used Vim for like 25 years, and I always refused to use Emacs because I was sure that Vim is the editor of choice. And at some point, I just saw that Emacs is objectively the better software. And I was fighting Vim all the time with all kinds of plugins to make it feel like Emacs and to have this all these features which are already built in an Emacs. And I feel like it's the same with Python. I'm constantly fighting with performance. I'm fighting with writing high-level API code, and just switching to a better tool to have all this in one package is better. But as always, new things just need to get more traction, and people have to try it out, and that's it. And I think what we said before, that it's nice that you can use Julia from Python and you can use Python from Julia, so both sides are possible. And calling C from Julia is really just a no-brainer without overhead. I think that makes it maybe a bit much easier, but who knows.
Yeah, okay, yeah, thanks. That was very comprehensive. Thank you so much. Vim is probably very eager by now to jump into the discussion, so I'll let him continue. Thanks again for these good points.
Yeah.
I'm not really sure what I point to add to the discussion, other than a couple of remarks I'd like to make. For the case of Python adoption, I do want to remind people that way back when, we're talking 2002, it had the support of the chief architects of both LHCb and Atlas. And so there was, of course, a big push from that side. Now, originally, it was only meant to be interactive access to the Gaudi framework, but that high-level support has been there from the beginning, which is different than what I see developing here from the grassroots. So there would be a different way that the adoption can or should happen. But the point I'd like to make is there is this project which is being started by Fazil, who you all know as the author of Kling, which I put this in the chat, and I think Benjamin forwarded this. And what he's trying to do is to abstract what Kling is and move these pieces into Clang, so in LLVM. And so, this might trickle down the other way back again into Julia as well. And what we have there is we're trying to have this ability of using all kinds of languages, say, for example, in a Jupyter notebook, both ways and back. And this is a 3-year project, and there's still some time to go. But right now, the languages that we have is Python, obviously. We have D and we have Lisp, and it would be absolutely great if there are Julia people interested in joining this project and making sure that all this stuff works for Julia as well. For this particular audience, in terms of adoption in HCP, since this is stuff that goes into LLVM and then trickles down back to Kling and then into Root, it means basically all of Root and probably most of the experiment frameworks would then be available in Julia natively if we can make this happen. So if anybody is interested, it would be great. In terms of how difficult it would be, since we already tried this out, this is from the past couple of days, to use CPPY through PyCall. Since PyCall provides you a good interface of mapping Julia thingies to Python thingies, and since CPPY knows how to do Python thingies to Kling thingies and basically libinterop, which is then going to be Clang REPL in official LLVM, it should not be hard at all. And to anybody who's enthusiastic and just looks at the code and says, hey, this is the straight shortcut from the Julia thingies to the Kling thingies without this Python layer. And then you would have a tool that is the equivalent of cxx.jl, but then without accessing LLVM directly and therefore not dependent on the specific LLVM version of Julia, and therefore in principle more maintainable. And then again, for this particular audience, it means access to your data because it's Kling, and so root of everything was there. Most likely access to all your framework, and that should really put you into business.
Thank you. That sounds like a very good, and thank you. Well, it's not an advertisement. I think it's very fair that you put on the link. It's on the chat, so I hope everybody can see it and open the browser if they want to check it out properly or offline. Thank you again for that. Very good. We still have a couple of minutes. I don't know if maybe. Yeah.
Maybe I could just. I didn't see any hands, so I'll just unmute. Let me video. Yeah, so I agree with almost everything that was said, especially about. I think the key point is about the ecosystem. You know, I mean, I've been increasingly convinced that this is a language that's far superior. It kind of marries the best of the performance C and the accessibility of Python. But I think the key thing is about the ecosystem. So we were just hearing about the, you know, tying into root and the frameworks, and that's great. But in terms of the analysis side, I mean, I think it's really the adoption, or it's so easy to integrate. There's a huge ecosystem around machine learning frameworks for Python, right? And so I was just wondering, I mean, thinking about building bridges and tunnels, and you want to know, you know, what does it look like? What are you building to this little sandbar, or is this huge thing that you're going to build to? So maybe outside of HEP, does anyone know or could give some insight on sort of, I mean, HEP is we think we're big, we're really a small community, and we're not a driver in a lot of this. And in terms of adoption of collaborations, I think the analysis, you know, the strong adoption by physicists who are doing analysis that are unconstrained by most of the collaboration aspects of, you know, integrating into large projects, software projects, I mean. So what would really drive, I think, people to play around with Julia and, well, not play around, but just adopt Julia and what their, you know, their precious time in developing some package are going to go to Julia, would be the availability of the ecosystem more generally. If I can't find things to link against, I have to then write them. And maybe if I write them natively, I do better, but I don't really want to spend that time. I want to do the physics. So does anyone have an idea of where outside of HEP the field is going in terms of adoption of Julia as a language, and whether the machine learning frameworks, you know, are when they will be equivalent to the Pythonic ecosystem around machine learning?
So on one side, they have far exceeded the Pythonic ecosystem. That's if you look at the SciML organization. So the scientific machine learning, there is a very strong drive behind neural ODEs and integrating the differential equation solvers with the language and with the automatic differentiation. So I think that is at least on par with Python. And so in those fields, the infrastructure is very, very good. And as I've shown, there's this diffeq Pi, I think it's called, which uses the whole differential equation solver ecosystem and makes it available to Python. But all of this is written in Julia.
Jerry, since you have not spoken yet, maybe I'll let you continue with that. There's probably many things that we will not manage to discuss today, which is a good sign anyway. But please go ahead.
No, yeah, this I was just trying to answer. Can everyone hear me? I don't trust Zoom very much. Okay, yeah, I just want to follow up on the question about where other fields are going on adoption of Julia. So there's this Klima at Caltech. They're running Julia on super computers modeling climates. I also know that there's astrophysics people, actually observational astronomy. They do like objects clustering with Julia, and I guess this has been advertised somewhere. Basically, Julia is the first dynamic language to reach, 1 petaflops, like being a pure language. And on the other side, which is how like different packages play with each other and an ecosystem about machine learning or statistics, what I want to point out is that like the reusability and extensibility of Julia code is really exceptional. Partly because kind of there's this drawback of foreign calls, like you write stuff in C++, so other packages you write has to inherit some kind of class that's glued back ultimately to C++. Also partly because of multi-dispatch, it makes it very easy to reason about, especially like what we do is we think about processing data. So it's really easy to reuse someone's library, like reuse two libraries that they don't mutually know each other. I will give one example. There's this library called measurements that knows how to deal with error propagation. So it has a number type defined that can do error propagation when you add, multiply, subtract numbers. There's also this package that solves differential equation, as we all know. So with minimum effort, really, you will be able to quantify errors on your solution of the differential equation solver, because all differential equation solver does is doing number crunching and stuff. Of course, it's hard to, when you have asymmetric errors, whatever, it's going to be more tricky to get it correct. But the idea is that you can have totally mutually they don't depend on each other or whatever, and they just work. So it's the ecosystem is more mature than if you're trying to find like a TensorFlow for Julia. It doesn't exist because it doesn't need to exist. We don't need 200K line of code in one repository just to do these few things. You can use existing stuff and it will just work.
Okay, thank you. That was quite certain. So we're getting to the end, and just be also nice to those that are in very, very far away time zones in Australia. We're going to stop very quickly. Benny, I saw you raising your hand, so if you have maybe a final comment before we need to offline.
I had a question about its use in astrophysics, because obviously astrophysics with AstroPy has led a lot how things like NumPy and other core bits of Python evolved. So I'm curious about it there. I also wanted to highlight that there is one question that came up on Slido, and that's a quite simple one that maybe we could take instead of my one, and we can take it on to Slack. But it's up to you, Eduardo, as chair of this. I think you're muted.
Okay, sure. Which one? There's 5 of them. 4.
They're all about the same. The basic question was, is Julia free and open source software?
Completely free and open source, yes, indeed, with proper licensing, or kind licensing, I guess. That's what people want to know. Jan, do you want to reply to that quickly?
Well, it's as free as Python. Short answer.
Yeah, I thought it was completely free. There's no right. It's a FOSS community, a FOSS and friendly community. All right, thanks so much. So in the interest of time, as I said, we will stop here. By all means, continue offline. There's this Slack channels. We also have Git channels, as you saw, for PyHEP, and we're a friendly community, as you have seen, so we can continue discussions there. I just want to share 2 or 3 slides with you, 4 or 5 slides with you to close the workshop. So let me do that. Interesting enough. Where did here you go. All right. So just a few slides. First of all, I wanted to show how diverse the registrations have been, gender-wise, but also in terms of collaborations that people have put on their registration. So you can see it's quite a few collaborations or experiments or groups or topics that have been that from people that have been attended this week, and this is fantastic to see. But by all means, we didn't want, we never had it, but we didn't want this to be LHC centric. Although we realize, and you can see from the statistics, that the very big experiments from the LHC in particular have big attendance, because it's just proportional. That's fair enough. What is really cool to see is the areas represented by the registrants. First of all, roughly half of the registrants are not from the LHC collaborations. And so this is what you see here, that we have almost 600 people from one of the LHC experiments, but you have bottom right, all the other ones, except where the HEP LHC is taken out. So you see HEP non-LHC, so that could be, for example, BESS3, BEL2, and some other experiments. So on GBAR, for example, there's quite a few people, about 100 people connected from those experiments. A huge amount of students and also collaborators from research institutes, which is excellent to see. And I have to say that maybe you don't know, but this is really the first year where we see the contribution from the neutrino community. And not only they have come to join the fund, but they have come in quite strongly this year. So this is really cool. We're really happy to have all of this diversity. By the way, in terms of registrations, I did not mention this, but this is just over 1,300 overall. So of course, not everybody was connected at the time. In fact, nowadays people connect more to sessions that I'm particularly interested in, and this is fair enough. We all have some kind of Zoom fatigue anyway. So now to finalize, some quick colorful plots. So where you can see here, you can't see the numbers, but you can see the share the cake more or less according to those physics areas that I have just mentioned. So HEP LHC, you see very big contributions from CMS and Atlas, also from LHCb. Atlas is also a relatively newcomer into play, by the way. So this is very nice to see. We have a huge community, as I said, a huge amount of collaborations represented from non-LHC, also from astroparticle and the neutrino community. I did not count, but there's probably about 20 experiments represented throughout the week here in terms of registrations. Again, if you want to look at also from the accelerator community, we had a few people attending heavy ions as well, even specifically on simulation and nuclear physics, so JLab and BNL in particular. And finalize also from some collaborators, some cosmology specific, so more on the theory side, maybe even computing. Here you see the root team, CNAF, Key4HEP, which is more for FCC maybe, at least for now. Instrumentation as well, even see proton therapy, muon tomography, medical imaging. So there are quite a few RD50 and 51 experiments at CERN. Quite a diversity we see everywhere across the various physics areas represented. So this is, by the way, the collage that we had about an hour ago, and I'm sure that there were quite a few more pictures uploaded, but there was no time to just refresh this picture. We will share in due time the whole picture. So to finalize, we thank you very much for your participation. For us, it was a great fun to organize PyHEP again. I hope it was for you as well. I hope you got something interesting. You saw that throughout the week, we had a diversity of presentations in terms of topics, in terms of level of expertise as well. So things which were tutorial more like to get started. Some that were HEP specific, some of them very expert level. We really hope that everybody got a bit of what they were expecting to have. So thank you very much. By all means, keep in touch through the various channels that we have indicated, and see you maybe at a future event.
So let's take the opportunity that Eduardo allows us to unmute to just clap for the organizer.
Thank you very much.
Thanks a lot.
On behalf of all the organizers. So this really is the end. And I hope to see many of you and discuss on Python, maybe even Julia in the future. Thank you. Bye-bye.
Bye.
Thank you. Goodbye.